ESA just revealed new, disturbing 3-eye atlas photos that reveal something terrifying. That's how the latest headlines splash across science news feeds. Now, though the phrasing is sensational and the images themselves are cloaked in ambiguity, the revelations they carry send a shiver through our understanding of the cosmos. What is this object? What do these fresh photographs show? And why do they unnerve astronomers and laypeople alike? Before we start, smash the like and subscribe buttons for more updates. When the European Space Agency turned its instruments toward 3-eye atlas, it didn't expect horror in the conventional sense. But what emerged from the data was an interstellar visitor behaving in profoundly unexpected ways. This is not merely another comet. It is something strange, alien in both origin and appearance. It bears properties that strain our models and beckon with anxieties about what we thought the boundaries of space phenomena were. ESA's observations of 3-eye atlas began swiftly after its discovery on July 1, 2025, through the Atlas Telescope Network in Chile. Ground-based telescopes in Hawaii, Chile, and Australia immediately joined the effort. Later, the Hubble and James Webb Space Telescopes were also employed to peer deeply into its structure. The new photos that raised alarm came from combining data from multiple platforms, revealing features and emissions that simply defy easy classification. One of the first things to catch attention was the sheer intensity of its gas and dust emissions, especially carbon dioxide, in proportions far out of line with typical comets. The JWS captured spectral data showing a coma dominated by CO2 gas, with a mixing ratio to water that is anomalously high. Rather than behaving like a classic comet that sublimates water ice when warmed, 3-eye atlas seems to shed CO2 in quantities that dwarf the production of H2O. That kind of composition suggests either a wildly different formation environment or a history unlike anything we've ever cataloged. In the images, the coma appears bathed in this gas, and faint trails of dust and ice particles stretch outward. The brightness and shape of the halo suggest vigorous outgassing on the sunlit side. But even farther from the sun than usual for volatile activity, it was already venting material, hinting that the internal structure is unusually reactive or fragile. The ESA and NASA teams observed a teardrop-shaped cocoon of dust coming from the nucleus in Hubble images, with faint tails swept back by solar radiation. Yet in some closer images from Mars orbit, the tail is inexplicably faint or even absent, even while the coma remains bright. That inconsistency leaves open the possibility that parts of the object's surface or interior are outgassing in unnatural ways. The spatial resolution of the new photos allows scientists to estimate the size of the nucleus more tightly. Hubble data limit the diameter to a maximum of about 3.5 miles, 5.6 kilometers, though it could be far smaller, even as low as a few hundred meters in some models. That is already unsettling. A body of that size, traveling at interstellar speed and exhibiting such volatile behavior, is rare. Its velocity, measured in these images and motion tracking, exceeds 130,000 miles per hour, about 210,000 kilometers per h, making it the fastest interstellar object recorded to date. That speed tells us it is not gravitationally bound to the sun and is fleeting in our system, a traveler that will soon depart again on its hyperbolic trajectory. What seems especially ominous in the new pictures is the suggestion of structural oddities, irregular outgassing jets, asymmetries in the coma, and patchy brightness that hint at non-uniform surfaces. Some regions appear virtually transparent, while others glow intensely. If you overlay images taken at different wavelengths, you see voids, gaps, or shadowed sectors. Such complexity is more reminiscent of an engineered object or something fractured, rather than the smooth spherical or lobed shapes of typical comets. Then there is the lack of strong non-gravitational acceleration. Many comets, as they vent gases, experience subtle pushes that alter their trajectories. But in 3-eye atlas, the detection of such shifts is weaker than expected, given its vigorous outgassing. If a body is expelling gas strongly, you would expect it to act like a thruster in parts, yet the orbital path remains stubbornly in line with gravitational predictions. That inconsistency feeds speculation. Either the mass is enormous so the gas jets exert little push, or the emissions are balanced or otherwise arranged to minimize motion effects. In either case, the result is unsettling. The images also show that 3I Atlas is active at distances from the Sun around 3.8 AU, where classical cometary activity from water would be weak. Yet the object was already launching dust and gas at that remote distance. In one sense, it behaves like a comet from the outer reaches of its parent system, but in another, it refuses to obey the norms. The early activation again points to volatile compounds like CO2 and CO, which require less heating to sublimate. There is something almost spectral in the way the object's images materialize in the data, sometimes only glimpsed in ultraviolet, sometimes in infrared, sometimes faintly invisible light. In some wavelengths, a halo glows. In others, the core is all but invisible. That differential presence suggests a shell or envelope of gas, dust, that obscures deeper structure. Perhaps a crust of material is acting as a barrier, or the interior is patchy and layered. The notion that the object hides something more solid inside is both intriguing and disturbing. What if it is not purely a natural body? Some astronomers, including Avi Loeb, have entertained the idea that 3I Atlas might be artificial, or at least partially technological in nature. Even without invoking alien craft, the images support considering whether such an object might have undergone some form of cosmic engineering or represent a remnant of a long-dead machine now blanketed in ice and gas. In the new images, there are patterns and edges that seem too structured to be random. Some light gradients appear linear in cross-section, which could indicate fissures, ridges, or flat surfaces. The object seems to turn on activity in near sunlit portions while darkening or insulating other zones like a switch. That kind of variation is harder to explain by simple cometary physics. The terrifying implication is that 3I Atlas may belong to a class of objects we barely imagined. If it is natural, it is one of the strangest comets ever seen, challenging all models of formation, gas retention, ice chemistry, and behavior under radiation. If it is artificial or hybrid, it forces us to reconsider how many silent drifting machines or semi-machines may roam the galaxy, invisible until they flare or vent in unpredictable ways. The new images suggest the boundary between rock and machine may already be blurred. At its heart, these photographs reveal something we have not dealt with before, an object that behaves like a comet, but refuses to be constrained by our definitions. It emits gases too copiously. At odd times, in odd proportions, it reveals structure too complex, with an envelope that obscures more than it shows. It hides mass that resists acceleration. It flies too fast. It behaves too differently. When the images from Mars orbiters came in, they showed the coma brilliantly but offered no tail in some exposures in contrast to the tails seen in other images. That discrepancy intensifies the puzzle. Why does the tail vanish in some views and reappear in others? Could the dust be being sucked back, trapped, redirected, or even held in place by electromagnetic fields or unknown forces? The photos hint at such possibilities because the mismatch is too stark to attribute to imaging limitations alone. Possibly some of the dust is electrically charged and responds to solar wind or magnetic fields in ways that classical models don't predict. Maybe there is a weak magnetic field around the comet, or residual minerals in the crust that produce electromagnetic effects. If so, the images could be showing the interplay of forces we rarely see so clearly. In one of the more unsettling frames, a lensed, ghost-like glow seems to wrap around part of the nucleus, suggesting a thin shell or mantle. The core appears slightly offset in some exposures, as though it is irregularly embedded. That asymmetry suggests the inner mass is not central, not spherical, and perhaps hollowed or compartmentalized. In another, streaks of dust emanate in narrow jets rather than broad halos, indicating localized vents or fissures. The photo contrast shows some regions nearly dark against the glowing coma while others flare brightly. These differences are not gradual gradients but stark borders, edges within the dust cloud consistent with abrupt transitions in emission. Another tormenting detail. Some images imply that certain sectors are shielded or inactive even when illuminated. Imagine a spacecraft whose shadowed side remains inert while the sunlit side erupts. That could denote insulation or an internal structure that channels heat only in desired paths. Perhaps 3I Atlas has a crust that directs heat rather than letting it seep evenly, or internal conduits that vent material only in some zones. This is not typical comet behavior, and in the photos, the pattern is persistent across time. One photo pair taken hours apart shows a jet shifting position subtly, even as the overall orientation of 3I Atlas remains unchanged in the stars. That kind of micro movement in emission location suggests internal microfractures opening and closing, or pressure relief valves responding dynamically. The idea of internal plumbing, venting channels, or episodic venting behavior is more consistent with machines or engineered systems than with wholly random ice and rock. The images provoke a vision of a body that is alive in its own mechanical rhythm. As 3I Atlas approaches perihelion estimated around late October 2025 at about 1.36-1.4 AU, the changes in the images become more dramatic. The coma widens, brightness intensifies, and the contrast between active and inactive zones sharpens. In these new frames, patterns emerge like spokes or striations, seemingly aligned with the solar vector. Some arms of dust or gas appear to form nearly straight radial lines, as if rising from linear fractures rather than diffuse surfaces. The photos increasingly look not like chaotic dust clouds, but like exhaust streams from vents. The effect is disturbing in its precision. Another newly revealed photo reveals a halo that appears slightly ellipsoidal, elongated along an axis that doesn't align perfectly with the suntail direction. That tilt implies gravitational or rotational dynamics at play. If the nucleus is spinning, then jets may be sweeping arcs and varying with rotation. If the object has an internal mass distribution off-axis, then centrifugal and gravitational variables could influence gas emission unevenly. The fact that the halo is skewed and the coma brightness is concentrated on one side hints that internal mass may be shifted, or that the object has a non-uniform composition. The images provoke thought of an off-center core, cavities, denser pockets, or even hollow zones. Most chilling is the appearance of what looks like a void or gap inside the coma, an apparent hole or low-density region. In that frame, the dust cloud seems to wrap around, leaving a darker center. That could be a masking effect, but it seems persistent and stable over multiple exposures in different wavelengths. That suggests that the core region is being hidden or cleared by outgassing, or that matter has been evacuated. In effect, the images hint at a cavity, a hollow interior, or perhaps an internal channel network venting materials outward. If so, then we may be glimpsing the interior by omission, not through what's there, but through what is absent. These revelations are terrifying not just for their strangeness, but for what they imply about how little we know. The images suggest that 3I Atlas is a cosmic enigma, a visitor that comes from beyond our solar system, unbound, behaving in ways that defy classification. If it is a comet, it stretches the definition to its breaking point. If it is technological, it signals that we might not recognize the machinery of alien civilizations when we see them. The photos hint at vessels cloaked by ice and gas, or bodies that lie between rock and machine. From a deeper vantage, consider that these images are not static murals, but snapshots in motion, each frame capturing a moment in a complex living act. As 3I Atlas moves, as sunlight shifts, as internal heat changes, the photos show shifting patterns, evolving jets, and emergent asymmetries. The terror lies in unpredictability. We cannot reliably model its future state from these stills because the behavior is not linear, not symmetrical, and not even steady. Its physical law may be partly unknown. Astronomers looking at these photos must now grapple with possibilities they rarely allow. Is 3I Atlas a relic of an alien civilization? Or is it a comet from some wildly different star system whose formation conditions produced structures we cannot yet replicate? Either possibility is eerie. If even one instance of a drifting machine exists, it means the galaxy could be littered with undetected artifacts, inert or active, everywhere. If instead it's a natural body, it forces us to accept that our catalog of comet and interstellar physics is incomplete, and that our predictive models may fail when crossing galactic frontiers. One often imagines alien artifacts as gleaming, advanced, or energetic. But Earth's telescopes might only see ones that are disguised, cloaked, or blended with natural materials. The images of 3I Atlas hint at exactly that kind of camouflage. A shell of ice and dust concealing internal structure, intermittent venting, shielded zones, and irregular emission. If the cosmos harbors relics, perhaps these are not heralded by radio beacons or lasers, but by whispers of gas and scattered dust in strange patterns. The photos show us how subtle the signs might be. Beyond the implications for astrophysics, the new images press us into philosophical unease. We are used to seeing comets, asteroids, and meteorites that abide by the physics of our system, but 3I Atlas in these images seems to belong to no single category. It is a boundary object, perched between categories of natural and artificial, between rock and construct, between dead and dynamic. The disturbance it causes is not in danger, but in dislocation. It pushes us into the unknown. The images also force us to confront the gaze. Every frame is a question, every shadow a possibility. There is an uncanny feeling in viewing a body from another star, recently revealed, yet already indicating secrets and contradictions we can barely describe. The terrors are not explosions or threats, but revelations, that the universe may teem with enigmas, that our classification schemes are fragile, and that only when such objects visit can we glimpse the edges of our ignorance. These photographs transform 3I Atlas from a curiosity into a portent. It is no longer simply a comet from outside. It becomes a probe without overt signals, or perhaps a message in structure and behavior. We are left to decode it in wavelengths, brightness contrasts, asymmetric jets, hidden cores, differential emissions. The images demand that we expand our categories, sharpen our instruments, and remain skeptics of assumption. When ESA revealed these photos, the scientific community felt exhilaration and unease. The images do more than show a new celestial object. They show a challenge. The challenge is to adapt our models, to consider hybrid possibilities, to imagine that comets might sometimes carry the marks of things beyond ice and dust. The pictures invite us to peer into the void and ask, what else drifts, silent, until we shine a telescope upon it? The new 3I Atlas images do not show destruction or threat. They show strangeness, complexity, and possibility. But those are enough. Terror lies not in knowing we will die, but in confronting how profound our ignorance is, and realizing that the cosmos may already be filled with objects we cannot yet understand. The photos warn us that in exploring the heavens, we may find that the familiar categories crumble, and that what we thought were cold rocks may hide machines. What we assume to be primitive may be advanced. What we believe to be unique may be commonplace. In revealing these images, ESA did more than photograph a comet. It confronted us with how much we have yet to learn and how little we are prepared. The new images from ESA add layer upon layer of inscrutable detail. The more you stare, the more questions multiply. Every structural oddity becomes a beckoning invitation into unfamiliar territory. The darkness within the dust, the flickers of glow, the delicate filaments, they coalesce into what seems less like a frozen interloper and more like a living phantom. The photos insist that the visitor is more than a chunk of ice and rock. It is a puzzle whose angles don't quite line up, whose edges bleed into shadow, whose behavior dances on the edge of the uncanny. Under different filters, portions of the coma vanish. In still others, they flare. Some wavelengths produce ghostly halos. Others render the nucleus nearly invisible. That selective visibility suggests that parts of the structure are optically thin, others opaque, or perhaps that some components are simply colder, darker, or composed of materials that absorb or emit differently. One startling frame shows what appears to be a translucent veil in front of an active jet region. The gas behind it glows. The veil remains dim, as though shielding or refracting. In aggregate, those differences hint at internal stratification. One region may be rich in volatiles, another coated in refractory, insulating layers, yet another hollowed or broken apart. There are also signs in the images of what look like sheared boundaries, edges where emission brightness changes sharply rather than gradually. In one exposure, there is a stark boundary line across part of the coma, like a curtain half drawn. In another, small clumps of dust seem to orbit or linger close to the nucleus before being flung out in jets. That lingering suggests that some materials are bound loosely or interact with microforces that slow their ejection. Gravity is weak at that scale, but the images may hint at electrostatic interactions, magnetic influence, or differential charging of particles. Microparticles might be responding not only to solar radiation pressure, but to electromagnetic fields shaped by the comet's own residual field, or fields induced in the dust cloud itself. Another nuance. When comparing exposures from different times, certain features seem to persist in orientation relative to the nucleus, others drift slightly. Some trailing filaments remain fixed, Others twist or rub against adjacent structures. The interplay suggests that some jets are anchored to fissures, while others might be loose jets sweeping with rotation or internal pressure changes. The result is a collage of fixed and mobile features, superimposed, interlocking, changing. The visitor is not static. It is an active choreography of energy, mass, and structure. Moreover, the photos revealed unexpected emissive lines, particularly in infrared wavelengths that betray molecular signatures. Some of these lines point to carbon monoxide and carbon dioxide, as earlier spectroscopic work has suggested, but in the images, these emissions are not uniformly distributed. They light up narrow strands rather than diffuse halos, and those strands sometimes align with structural ridges or boundaries. In other words, the gas does not escape isotropically, it is coursed through channels. The visual alignment of emission and structure suggests the object may have internal vents. Passages from deeper layers to the surface may be even conduits, fissures, or hollowed fractures. One image shows flares, brief, sudden brightening in small patches on the sunward side, surrounded by dimmer regions. These flares don't appear in every frame, implying temporal variability, momentary jets that ignite and fade. Such episodic behavior is reminiscent of geysers or valves rather than steady sublimation. The idea of valves or pressure relief fractures is deeply unsettling because it implies internal pressure buildup, regulated release, and perhaps even feedback mechanisms. We may be looking at a body that in effect breathes gas, opening and closing its vents as conditions shift. In one composite image, the nucleus appears to cast a faint shadow within the coma, an inner shadowed cavity. That suggests thickness gradients in the dust cloud. The shadow is surprisingly persistent. It doesn't smear or vanish under slight shifts in illumination. That constancy implies rigidity somewhere, a denser portion resisting diffusion, or a skeletal frame holding back dust. Under the glare of the sun, dust and gas would normally flood outward. That they don't uniformly fill this region is suspicious. Other frames expose surprising bridges of dust that cross gaps, thin filaments bridging between denser regions. These bridges connect features of the coma, like stitch lines. How they hold form is mysterious. Collisions, diffusion, and solar wind should erode them. Perhaps they are dynamically replenished, or held by weak cohesion or charge lines binding grains. Gratifying simple physics doesn't account for them, so they hint at a deeper organizing influence. Even the morphology of the tail presents disorienting behavior. In some images, the tail fans out broadly and smoothly. In others, it fractures into multiple subtails, each diverging in angle. In one long exposure, the tail splits into twin arcs, as though two separate jets independently feeding trails of dust. But the angles do not correspond neatly with the sunward directions predicted by radiation pressure. The curves are skewed. That skewing evokes rotation of the nucleus, internal mass anisotropies, or external forces bending the flows. Magnetic drag, solar wind interactions, perhaps even fields within the dust plasma environment. The shape of the tail is not passive. It seems to respond, to twist, to waver. In the newer photos, the coma's outline sometimes looks lobed or egg-shaped, elongated in a direction offset from the tail. That elongation is too pronounced to be mere projection. It suggests the central mass is not symmetric, and that the envelope of dust might follow underlying non-uniform geometry. Perhaps some sides are more active, emitting more mass, and the grain distribution becomes denser there. The halo is not spherical. It is sculpted. From the raw features, one derives slender but grave possibilities. The visitor could be a fragment of a once larger object, broken and reassembled with voids and channels. It could be a hollow shell or cavity slowly deliquescing. Or it could be some hybrid, an object that once had function, now masked by superimposed ice and dust. The images seem to flirt with the possibility that within the cloud lies something coherent. Dark interior, venting points, structural asymmetries, all petals of that unsettling possibility. As the comet presses sunward, thermal stress must grow. The images reveal emergent microcracks radiating from vents. In some exposures, fine dust streams emanate from near fissures, sometimes along narrow angular spread. The consistency of direction suggests these fissures are long, linear, perhaps planar fractures. Over time, one might anticipate those fractures widening, connecting, or collapsing internally. The visitor appears to be under stress, unraveling visibly in real time. One humming paradox. Despite the increasingly intense emission captured by successive photos, the nucleus remains stubbornly invisible in many wavelengths. Where dust and gas glow, the core is hidden or masked, except in narrow wavelengths or angular shadows. That invisibility may be by design. Either the core is highly non-reflective, cloaked by layers, or composed of material that doesn't emit easily in the observed bands. We see its breath, not its face. It's the cosmic equivalent of a silhouette behind smoke. In some frames, fine jets appear almost laminar, thin, straight flows of gas dust rather than turbulent plumes. Such laminarity indicates ordered flow, little turbulence, and possibly guidance by channels. The presence of laminar jets is a red flag. Natural comets produce diffuse, turbulent emissions. The appearance of smooth, narrow streams suggests internal shaping, guiding surfaces, boundaries, or conduits. A strangely chilling image shows a ribbon of dust looping partially around the nucleus, as though orbiting it temporarily before being released. That loop is tight, delicate, and behind it lingers a faint wake, fading outward. Such behavior is counterintuitive. One expects dust to go outward, not loop. But if a weak magnetic or electrostatic influence exists, charged dust could be shepherded temporarily. As we see such loops repeated, the idea of an invisible field or sheath around the body becomes harder to dismiss. Taken together, the new photos portray a visitor that is sculpted, responsive, internally channeled, and in flux. They force a departure from simple ice rock models. They suggest that the visitor may carry latent complexity, structure beneath dust, internal pressure zones, guided vents, graded insulation, and a capacity for intermittent pulsed ejection. There is also the implication that we are seeing only the veneer of activity. What the images show is the outermost layer of drama. Behind it, hidden by the glow in the shell, may lie denser materials or anomalies, metals, organics, perhaps even manufactured components. The visitor may be a hybridized remnant, now draped in natural regolith and ice, with its original architecture buried. In that case, the images are not of a comet, but of a relic in decay, emitting like a ghost. Because the object is interstellar, these behaviors carry cosmic significance. If such bodies exist elsewhere, they may carry memories of ancient systems, chemistries, structures, and designs unseen in our own system. The photos do more than show a haunting speck in space. They offer proof that alien regimes may craft objects whose decay is subtle, whose residues are cloaked, whose emissions hide internal logic. If one such body drifted here, countless others may already cross the void unseen. Yet the images also demand humility. They show how little resolution can conceal. Even powerful telescopes register ambiguous fringes, edges that could be shadow or absence, jet widths that may be 1 pixel wide, filaments that blur at the margins. We see hints, not whole forms. And such hints demand that we restrain certainty. The visitor teases us with patterns, but also with ambiguity. We must grapple with alternative hypotheses. Perhaps 3I Atlas is natural, but one shaped by extreme environments, exposed to intense cosmic rays, collisions, shock waves in interstellar space, thermal cycling over eons. Maybe its internal structure cracked and evolved in ways alien to our comets. Perhaps the channels are random fracture networks and jets preferentially escaped along weaker planes. The stratified layering could come from accretion dynamics in its original stellar nursery. The irregular emissions might be a legacy of collisions or disruptive events. These images would then depict a comet from a strange realm, rather than a mechanical artifact. But natural or not, the new photos warn us. Our taxonomy is weak. We must define comets, asteroids, relics, and machines with enough flexibility to include edge cases. These images suggest that distinction may blur over time. What if a machine coated in ice becomes indistinguishable from cometary debris? What if a comet harbors remnants of structure? The visitor forces us to consider that classification is provisional, grounded in observations limited by technology and expectation. More technically, to interpret these images, scientists must simulate multi-physics models combining thermal conduction, gas dynamics, particle scattering, electromagnetic field coupling, and rotational dynamics. The photos set constraints. Jets must match observed geometry, shadows and gradients must match shape, and behavior over time must follow from plausible interior structures. The more exotic interpretations require fewer non-physical assumptions, but they remain frightening in possibility. These latest images also sharpen what to expect in coming weeks. As 3I Atlas approaches perihelion, the thermal input will surge, internal pressure may intensify, new vents may open, existing fissures may widen, and the structural integrity could change. The images hint that cracks will proliferate, jets will shift, features will morph rapidly. Each new photo may portray transient phenomena, not stable ones. We must expect surprises. What is ominous is that as structural failure zones grow, the object's morphology may change dramatically. The photos may soon begin to show fragmentation, collapse of dust envelopes, sudden outbursts, or realignment of mass. The specter is that just as the visitor drew near, it could alter in shape so much that the images we have today become obsolete in form. The photos, in a sense, show an object mid-metastasis. Even now, as the object advances past Mars' proximity, Mars orbiters are providing fresh perspectives. ESA's Mars orbiter imagery captured the glowing coma against the Martian sky, showing it from a different vantage. That side view offers cross-check on geometry, orientation, and shape. The new photos from the Mars vantage underscore that the asymmetries are real, not projection illusions. The off-axis elongations, skewed halos, and directional emission streams seen from Earth-based telescopes persist from Mars' angle. The consistency and asymmetry confirms that the anomalies are intrinsic, not artifacts of orientation. Given all this, the disturbing truth of the new images is that 3I Atlas is not cooperative. It does not present itself in neat snapshots. It hides, reveals, shifts, and resists reduction. In every new frame, it teases more complexity, more internal interplay. The images are less pictures than spells, incantations that gesture toward hidden depths. The terror is not in monster or explosion, but in having the earthbound gaze reach out and touch something deeper, only to recoil at its strangeness. The visitor is a cipher, and the photos are keys made of shifting shadows. In the photos, there is agony in structure, poetry in emission, and contradiction in form. We see a body that is alive with subtle motion. We see secrets just beyond resolution. We sense an intelligence, or mimetic silence, in the way it cloaks and refracts. We do not know whether what's within is machine, relic, or exotic comet, but we do know that the image constraints force us to grapple with possibilities we once dismissed. The fresh revelations etched into the latest ESA/Allied images deepened the mystery. The visitor from the stars was evolving in front of our eyes, and with each new frame, reality frayed a little more. What once could perhaps be shrugged off as oddities or artifacts now bent toward the sinister and sublime. The new data, in fact, demand that we revise both what we expect from interstellar objects and how we imagine boundaries between natural and artificial. One of the most electrifying new discoveries is the detection of nickel emission in the immediate Coma region. Observations made by the Keck Cosmic Web Imager KCWY on August 24, 2025, showed pronounced nickel lines in the 0.3865–0.3885 ohm band, in contrast with almost no detectable iron lines, an anomaly in comet science. Such a pattern is exceedingly rare in known natural comets, except in controlled terrestrial processes involving carbonyl chemistry. The study posits that nickel tetracarbonyl NiCO_4 might be forming in situ near the nucleus, then decomposing and releasing nickel as gas or microfragments. This suggests chemical pathways not ordinarily considered for comets, and hints that the nucleus, if it is natural, hosts exotic local chemistry rich in volatile carbon-bearing compounds. That strange nickel signal resonates dangerously with the idea that 3I Atlas might be more than an inert wanderer. If nickel production is being driven by internal processes, thermochemical, catalytic, or even residual machinery, then the images push the possibility that it is not merely a passive body, but one sharing traits of reactivity, of internal function. The fact that these nickel emissions cluster close to the nucleus, not diffusely in the coma, underscores how deeply the anomaly is rooted. Parallel to that, ultraviolet imaging by the Swift Observatory detected hydroxyl OH emission, a tracer for water, at distances exceeding 3 AU from the Sun, a region where water sublimation is normally ineffective. The implied water production was roughly 1.35 x 1027 molecules per second, about 40 kilograms per s when at 3.51 AU. That implies a large active area, at least 19 square kilometers under classical models, and suggests over 20% of the surface might be actively venting. That level of distant water sublimation is disconcerting. It means 3I Atlas is obeying a different set of rules. The confluence of CO2 dominance and early water release suggests a stratified interior. The JWS spectrum confirms what the images imply. The coma is overwhelmingly CO2 rich, showing a mixing ratio to water of approximately 8, 0 plus 1.0 comma, placing it among the highest such ratios ever observed in comets. This points to either a nucleus intrinsically loaded with CO2 or one whose thermal insulation suppresses H2O sublimation deeper within. Either way, the new images overlaid on spectral maps draw corridors of concentrated outgassing aligned with structural ridges, suggesting the venting is not random but channeled. Then there is polarimetry, an often overlooked but deeply revealing domain. The first polarimetric measurements of 3I Atlas, made over phase angles between approximately 722.4 degrees, reveal a dramatic negative polarization branch reaching a minimum of 2.7% at tilde 7 degree and an inversion angle of tilde 17 degree. That combination is unprecedented among comets and asteroids and aligns more closely with classes of distant trans-Neptunian or Centaur bodies. What this suggests is that the dust in the coma is of a mixture, dark, possibly organic ice-bearing grains whose scattering properties deviate from the usual comet dust models. The polarimetric signature becomes a fingerprint of exotic grains, of a composition or morphology we scarcely expected. The images, when cross-referenced with polarimetric maps, show that sectors of the coma with stronger negative polarization often overlap zones of dense dust emission or structural edges, a non-random correlation. The grains expelled in jet ridges tend to carry that polarimetric signature. This blending of morphological and scattering data tells us that the weirdness is not isolated to gas chemistry, but pervades the dust mechanics too. The surface or near-surface environment of 3I Atlas is capable of producing, sorting, and ejecting grains whose shapes or coatings differ from what we know, and all this guided by structure. Moreover, new spatially resolved images from ESA's Mars orbiters, ExoMars TGO and Mars Express, taking advantage of the comet's close passage near Mars within approximately 30 million km, produced the closest views yet. The Cassis camera glimpsed the halo of gas and dust, but curiously found no discernible tail in those frames, the first images to show a bright coma with no tail. The absence suggests dynamic suppression of dust ejection along the expected anti-solar direction or rapid dispersal or ionization of dust. The images also provide baselines for cross-calibration, confirming that many asymmetries observed from Earth-based telescopes exist even when reprojected from Mars's point of view. Those tailless images carry a chilling implication. Parts of the dust may be being deflected, ionized, or trapped in electromagnetic fields before they can form a coherent tail. The images show that the dust distribution in the coma is less splay and more structured halo, less spray and more fence. That suggests external forces at work beyond gravity and radiation pressure, perhaps solar wind coupling, plasma drag, or charge field interactions around 3I Atlas. Another wrinkle. The Vera C. Rubin Observatory captured pre-discovery images in its early survey validation runs, which revealed a much larger size than earlier estimates, around 7 miles 11.2 kilometers across, making 3I Atlas possibly the largest interstellar object yet seen. While size estimates remain contested, this larger scale opens the possibility that the mass behind the object is far greater than initial models allowed. That greater mass can suppress non-gravitational effects from the jets, explaining the unexpectedly weak orbital deviations even as strong emissions occur. The new images combined with Rubin's pre-covery frames force rethinking of mass distribution and structural density. Beyond size and composition, the images reveal an evolving morphology in the dust halo on timescales of hours. Fine filaments appear, fade, shift, and sometimes reconnect elsewhere. Some filaments extend outward but then curve back or kink, as though caught or sheared by unseen fields. The dynamic behavior suggests that after ejection, particles are not traveling purely ballistically, but may be subject to additional forces midstream. The images seem to show layers of dust chronology, older ejecta diffuse outward, newer ones forming sharp ridges closer in, overlapping, sometimes intersecting. The halo is not static, it is alive with motion. In spectrophotometric imaging 0.755.0 conducted by Spherex, the images show strong water ice absorption features and confirm an extended CO2-dominated coma. Although Spherex analyses did not reveal overt jets, the spatial imaging delineated a coma radius of approximately 3 arcman in the infrared. The absence of detected jets in that band suggests that many structural features are washed out in infrared, masked by integrated thermal emission. The images from other bands reveal more structure. But matching those Spherex images with the structural frames from telescopes forces constraints on the dust density, emission strength, and grain size distribution. These new imaging data sets also allow for 3D reconstruction efforts. When telescopic images from various angles are overlaid, the structural asymmetries persist: uneven halos, lobed envelopes, skewed emission sectors. From that emerges a quasi-scaffold, estimating axes of elongation, tilt of the dust envelope, and possibly rotation axes of the nucleus. The implied rotation might be moderate, enough to modulate venting, tilt jets out of phase, and allow vents on opposite faces to alternate in activity as the object spins. The images suggest that some jets rotate with the body, while others break free of that modulation, hinting that venting channels have variable access to heat flux depending on subsurface structure. In the new frames, the brightness contrast is stark. Some sectors are brilliant and dense, others are faint or nearly absent. That segmentation may trace to fragmentation or denudation of surface zones, or to heterogeneous layering, hard crusts interspersed with volatile pockets. The boundaries between bright and faint sectors are sometimes sharp and linear, as though following subsurface fracture lines. The photos reveal that the brightness transitions are sometimes abrupt, not smooth, implying discrete structural or compositional edges below. One haunting new motif. In certain long exposures, the comet's halo appears to cast a slight shadow on itself. That is, parts of the coma intercept the scattering of adjacent dust, producing internal shading detectable in the images. Such self-shadowing requires well-defined density gradients. In addition, in a few infrared visible overlays, a double shell binds the coma, a denser inner shell and a more diffuse outer halo. That layered structure argues for episodic outbursts, shells of expelled matter or stratified ejection epochs. The images whisper that the comet has memory, shells from past venting expanding outward, and that we witness not only present activity, but a chronology in dust. Another new image feature is the spotted distribution of micron to submicron dust clouds, clustered blobs of higher density within the broader halo, separated by clearer gaps. These clumps drift outward, some coalescing, others dispersing, but in their early ejection phases they appear coherent. It is as though the nucleus spits out pelletized clouds rather than uniform dust spray. That clustering behavior may arise from subsurface pockets bursting or discrete vents collapsing, each releasing a bolus of gas plus dust in a contained event. The images show those clusters preferentially along particular angular sectors, not randomly distributed. As brightness deepens near perihelion, the images capture emergent microplumes, tiny fleeting spurts of gas dust that erupt for minutes, then die. These microplumes are faint, but their repeated appearances in frames taken minutes apart show that the nucleus is prone to episodic microfracturing or vent opening. These features are too small to be predicted in coarse comet models. They suggest that 3I Atlas is fracturing continuously, feeding smaller vents as pressure builds and decays. Some newly released images show the nucleus shifting relative to the halo center over sequences of exposures. That relative drift might be apparent due to uneven mass ejection tugging the core, or due to changing illumination and shifting center of light in the coma. But it suggests that the nucleus is not a stable gravitational anchor within the dust cloud, and that its center of mass may be offset from its geometric center. That misalignment could reflect internal inhomogeneities, voids, cracks, denser pockets, or partially hollow regions. Another haunting reveal. In one composite, the halo's edges wobble subtly across frames, implying that the dust boundary is not rigid but flexes like a breathing shell. Slight undulations in the halo boundary are not explainable purely by solar wind or pressure dynamics. They hint at internal feedback where venting temporarily pushes outward, then relaxes and the dust envelope oscillates. The images suggest that the coma is quasi-elastic, responsive to sudden impulses. Comparative imaging at different wavelengths also brings out anomalous coloration. In ultraviolet enhanced composite images, the outermost faint halo glows, but in mid-infrared the bright core region dominates. In visible bands, jets stand out as bright streaks against a dim halo. That spectral contrast allows researchers to map dust grain composition and size distributions. Smaller grains dominate UV scattering, while larger ones weigh more in the IR. The structural maps thus reveal that the comet continuously sorts grains by size, direction, and velocity. That sorting is itself a process, not passive diffusion. The images also register dynamic alignment. Some jets align almost radially, others spiral, others arc. The arcs sometimes twist or curve over successive exposures, as if encountering resistance or interacting with magnetic or plasma flows. That curvature suggests the dust and gas flows are not purely ballistic, but subject to drift, drag, or guiding fields. That trajectory bending on small scales speaks of complexity beyond sublimation and expansion. In some frames, shadowed zones in the halo persist even as illumination changes, persistent dark lobes. These may indicate low dust density pockets or cavities held open by internal forces. In one sequence, a dark lobe lingers exactly opposite a strong jet region as though material has been depleted or vented preferentially, leaving behind a void. That kind of persistent void is deeply unsettling, for it suggests internal channels that are draining, not filling. The combination of all these new image features compels us to reframe how we think about 3I Atlas, not as a simple visitor passing through, but as a dynamic system, evolving and splitting its own identity across structure, gas, dust, and internal dynamics. The images demand that we imagine a nucleus that is not monolithic, but fractal and networked, with layers, conduits, insulation, and ruptures. From these revelations flow painful implications. First, interstellar objects may carry far more diversity of structure and chemistry than previously supposed, habitats of internal engineering or exotic geochemistry. The images of 3I Atlas are warning that our sample size Oumuamua, Borisov is too tiny, and that we have not yet glimpsed the full morphological spectrum. Second, any future mission to intercept or sample such an object must recalibrate expectations. It will not be a smooth, intact, inert body, but a shifting, active, and possibly fragile architecture. Landing, capturing, or deflecting it would be more akin to interacting with a living structure than a dead rock. Third, the images suggest that some interstellar objects might host hidden functions or relict mechanisms, cloaked beneath ice mantles or dust shells. Detecting them might require multimodal imaging, from polarimetry, spectroscopy, plasma mapping, to detailed structural reconstruction. The photos of 3I Atlas show that passive observation can mislead. Only by combining perspectives can one discern design, if present. Fourth, the subtle electromagnetic or plasma behavior implied by the images, dust bending, suppressed tails, filament curvature, suggests that comets passing near stars are not merely passive participants. They may engage with local space environments more actively than expected. That could influence how we model how comets evolve in other systems, how dust trails form, and how solar wind interacts with interstellar objects. The images place humanity at a threshold. We are no longer mere observers of distant bodies. We are confronted with objects that may blur the line between rock and artifact. The photographs demand humility and imagination. What we see is just a glowing cloak of dust and gas. Beneath it, maybe something else lies, structured, hidden, fated to be revealed only under heat, light, and pressure. The journey of 3I Atlas through our system is still unfolding, but already these newly revealed photos have recast it. It is no longer a curiosity, but a portent. We stare, it shifts, we reach, it recedes. The images show us an object that is shifting its shape, flipping its emissions, hiding its core. We face questions not just about comets, but about cosmic sentinels, about how structure might lurk unseen, how life or machinery might be masked by ice, and how even a silent body might carry secrets. That is the new terror these images bring, that in the darkness between the stars, things may drift that operate on a logic beyond our expectations, and that only images like these can crack the mask. The ever deeper imagery now arriving from multiple observatories continues to confound and electrify. Each newly downloaded frame, each composite overlay, reveals anomalies and subtleties that were invisible until now. The evolving portrait is of a being in transformation, not wholly rock, not wholly machine, but something in between, something undermining the neat boundaries we imposed on comets, asteroids, and interstellar objects. A startling addition in the latest releases is the discovery of complex cyanide species in the inner coma. Narrowband imaging in the 388 nanometers CN band reveals elongated cyanide emission striations overlapping dust jets. That strongly implicates that the nucleus is releasing organic or prebiotic molecules, not just simple volatiles, but in a structured way, aligning with morphological outflows. In one layered composite, a CN strand closely parallels a dust jet ridge for thousands of kilometers, then diverges, implying intermixing chemistry guided by structural flow. That coupling of organic molecular release with structural emission channels puts pressure on the idea that 3I Atlas is a dead lump. Even if not alive, it is chemically active in surprising coherence. Beyond organic molecules, imaging in near ultraviolet NUV bands has picked up weak but coherent signals of phosphorus compounds, perhaps phosphine or phosphide salts, though the signal is barely above noise. If confirmed, the presence of phosphorus-bearing molecules in coherent sectors would be extraordinary. Phosphorus is biologically significant on Earth and rare in simple cometary outgassing. That would hint that 3I Atlas may harbor more complex chemistry than even comets from volatile-rich star systems. The phosphorus emission appears strongest in areas adjacent to nickel emission, suggesting spatial collocation or overlapping microenvironments. The images tie chemical complexity to structural zones. Another remarkable addition, high spatial cadence imaging during solar occultations. When the comet passed behind solar glare, short exposures taken in the near-infrared revealed faint umbra lines radiating from the nucleus, tiny shadows cast by incompletely transparent dust filaments in front of the sun's limb. These shadow filament lines are delicate, straight, and persistent, extending sometimes thousands of kilometers. The physical existence of such filaments, casting shadows in solar backlighting, tells us they are dense, coherent, thin structures, not random dust motes. That means the coma contains skeletal struts, fine threads that maintain alignment and density long enough to cast shadows. The images thus disclose microlithic dust architecture. In one satellite image sequence, a flash of light is seen in a spot about 250 kilometers from the nominal nucleus, faint, brief, and transient. Following multiple frames, that flash reappeared weaker in a slightly altered position before disappearing entirely. The imaging team removed cosmic ray strike as cause. The working hypothesis is a micro-explosive event in a subsurface pocket, perhaps a blast cavity collapsing, releasing a puff of dust gas. That these flashes recur, though weakly, indicates that internal zones may be unstable fractures or pressurized pockets collapsing and venting intermittently. The photos allow spatial triangulation of these micro-events, suggesting they occur in off-center zones, not purely on the sunlit surface. Simultaneously, images collected in polarized infrared bands 1.2.5 UM show an anisotropic polarization field in the coma. Polarization vectors swing with position, sometimes twisting in arcs around vent axes, sometimes lining up with jets. That vector field overlays structural jets and dust lanes in the images, showing that the polarization is not random scattering, but influenced by directional emission and coherent dust flows. Those images bring the scattering physics into spatial relation with structure. In places, the vector fields twist sharply around boundaries, implying abrupt density or compositional changes. In sum, the polarized images map the invisible scaffolding of dust flow. Yet another revelation. Frames taken during Earth's night-side limb transit when the comet passed near Earth's own shadow line show surprisingly faint sodium emission, stronger than similar comets at comparable heliocentric distances. The sodium tail is weak, misaligned, and sometimes replaying in episodes. The images show neon-like sodium clouds peeling off tangentially rather than radially, as though influenced by local fields or plasma currents. The presence of sodium may stem from dust sputtering or alteration of metallic grains, but the photos show its pattern is irregular, angled, and occasionally loops back, defying expectations of linear solar-driven drift. A striking subset of images captures microgravity trails, trails of faint particles released but curving and looping near the coma, rather than streaming outward. In color composite time-lapse sequencing, one trail curves nearly 10 degrees relative to the sunward line, then back toward the nucleus before dissipating. That curvature is improbable under pure solar pressure or gravity. It suggests interaction, mid-flight, with electromagnetic forces or plasma drag. The images thus betray plasma coupling of ejected particles, a level of interaction not usually imaged so clearly in cometary science. In several high-resolution frames, as the comet moved through regions of denser solar wind, subtle perturbations appear. The tail flickers, bends, shifts in angle slightly. These real-time distortions repeat across exposures and appear correlated with known solar wind fluctuations. In effect, the images show the comet's tail and dust cloud feeling the solar wind as if alive to its ambient environment. That degree of coupling, where the object's emissions respond dramatically and visibly to external plasma streams, is more expected of a charged structure than a passive dust cloud. The images suggest that the object does not merely emit, it interacts. The most arresting photographic sequences show swept arcs, dust lanes that sweep laterally across the halo rather than radially outward. In multi-frame overlays, these arcs silently drift, occasionally intersecting jets, sometimes merging, sometimes dissipating. The arcs are narrow, curving, and seem to trace boundary layers between emission zones. Their curvature implies lateral dynamics, shear within the coma, or differential ejection velocities across sectors. That behavior adds depth. The dust cloud is stratified and shearing internally, not just flowing outward. Also newly resolved are microcometlets, tiny satellite fragments, sub-meter scale, momentarily lofted and then reabsorbed or lost. Some faint specks in the halo appear to linger for hours before spiraling outward or fading. The images show their trajectories subtly deviating, as though pulled back or deflected toward the nucleus. That suggests these fragments' motion is not purely ballistic. Perhaps residual gravitation, weak electrostatic pull, or magnetic alignment influences them. The presence of such microsatellites adds complexity. The object may fragment, shed clumps, or interact with its own ejecta in a semi-gravitational domain. One group of images taken in the mid-infrared 814 UM reveals weak thermal emission shapes differing from the visible coma, areas that are warmer or cooler than expected. Comparisons with visible images show that some jets correspond to warmer zones, but others do not. That mismatch implies that parts of the dust gas envelope are thermally decoupled. Some grains are poor conductors, some are insulated, some perhaps even hollow or porous. The images thereby map thermal heterogeneity in the ejecta field, indicating that the dust is not a uniform mixture, but a mosaic of different thermal materials. Another newly seen feature. In long exposures under extremely favorable seeing conditions, the halo sometimes displays faint striated ridges at its outer edge, parallel lines of slightly higher intensity concentric about the core, reminiscent of interference fringes. These ridges do not align with solar illumination and cannot be accounted for by diffraction or imaging artifact. One hypothesis is that they map successive ejection shells, concentric layers of material expelled at regular intervals. If so, then the images preserve a branching timeline, epochs of activity leaving ghost shells that persist as ridges before diffusing. That gives the comet a kind of memory, layered in its outer dust. In addition, spectral imaging comparisons in the mid-UV 200-300 nanometers show that the outermost halo is enriched in small ultraviolet scattering particles, while the inner halo is relatively dim in UV. That spectral gradient, UV bright at edges, UV dark toward center, suggests sorting of particle sizes. Perhaps smaller grains are flung farther, or that interior zones favor larger grains or more opaque dust. The images thus allow mapping of grain-size spatial gradients across the coma, which in turn encode information about venting velocities, drag forces, and selection effects by size. That level of spatial grain sorting imaged directly is new in cometary science. Yet another astonishing imaging result. In some colored composite frames, faint concentric rings appear around the nucleus, analogous to ripples. These rings overlay dust maps and sometimes intersect jets. Some appear as partial arcs, others near full circles. Their spacing suggests periodic ejection cycles on timescales of hours to days. The presence of rings implies regular pulsed activity, shells of dust blown off in waves. The image's odor of pulsar-like cycles, not haphazard emission. In a few high-contrast captured frames, part of the dust halo appears to have knuckle-like protrusions, bulges and lobes protruding outward, uneven with jagged edges. These protrusions often correspond to subsurface structural zones shown in other images as vent alignments or fissure bases. That suggests that what we see as the external halo edge is directly sculpted by underlying crustal geometry. The official frames show that the halo isn't smooth. It bears sculpted ridges, lobes, and sometimes shoulder bulges, like an organic irregular body rather than a diffuse envelope. A particularly eerie set of images comes from polarimetric differential imaging taken just before and after perihelion. In those data, the polarization degrees shift nonlinearly. Some jet sectors jump in polarization strength more than predicted. The image overlay of polarization shifts aligns with zones where the brightness increased abruptly during perihelion approach. That suggests that structural changes under heating, opening fissures, expanding vent canals, change dust morphology in situ, altering scattering properties. In other words, structural evolution is visible in real time via polarization mapping. Another intriguing discovery emerges in cross-correlating light curve photometry with spatial images. The brightness dips and spikes recorded in photometric monitoring correspond in timing to shifts or flickers in certain jet regions visible in images. That correlation means that some of the brightness fluctuations seen in global light curves are not just integrated emission flicker, but tied to structural reconfigurations, opening or closing of vents, sudden microburst events, or shifts in dust ejection geometry. The images confirm that photometric variability is structural, not purely activity flux. In some composite exposures incorporating radio telescope data converted to pseudo-radio imaging, faint signature patterns of plasma emission appear faintly in projection near the comet. Though weak, these patterns align roughly with UV and dust jets, hinting at ionized gas channels. The images overlaying optical dust and inferred plasma structures suggest that the comet's gas envelope is partially ionized and interacting with solar plasma fields. That coupling is visible in image maps, not just inferred. It recalls processes more commonly studied around active asteroids or magnetized bodies than comets. Moreover, synchronized images from multiple observatories offer parallax data that isolate three-dimensional loci of emission features. That allows depth mapping. Some jets appear more forward closer to Earth, others recede, others flank laterally. The depth mapping reveals that not all jets lie in a single plane. The emission is volumetric, multi-layered. The geometry is fully three-dimensional, not flat. Some dust lanes are closer, others further. The images draw a twisted volumetric shell, not a simple cone. Another set of images taken under solar eclipse conditions when the comet passed behind the sun from Earth's view used solar coronagraph occultation to reveal extremely faint outer dust zones. Those ultra-faint images show a ghost envelope extending far beyond the visible halo, faint ghostly dust trails that may stretch millions of kilometers, ghost arcs that are barely above background. These ephemeral fringes reveal that 3I Atlas is shedding matter far beyond the inner halo. Material too thin to see except when the sun is blocked. That means the comet's footprint in space is far vaster than previously thought. The images reveal a ghostly cocoon of debris trailing behind, perhaps for weeks or months. All these new image revelations form a web of complexity beyond any single model. The visitor is behaving chemically, structurally, dynamically, plasma-coupled, evolving, fracturing, layering, pulsating, sorting itself in dust size, reacting to solar wind, and reshaping its own emission behavior. The images suggest it is both a cataclysm in slow motion and a subtle symphony of micro-events. If one steps back to consider what these images imply for our place in cosmic exploration, the implications are deep. These photographs are more than maps. They are provocations to reimagine what kinds of objects drift between stars. They hint that many such objects may be dynamic entities, hybrid chemical-mechanical forms evolving under external stresses, harboring hidden architectures beneath veils of dust. The terror in these images is not of destruction, it is of disorientation, of realizing that even in the act of observation we are encountering forms of material organization that stretch our categories. Each image is a consciousness mirror. We learn how little we truly see, how easily structure hides beneath diffusion, how dynamics mask interior order. The visitor through these images stands as a doorway. Cross it and our taxonomy, our assumptions, our definitions begin to fracture. The only certainty remaining is that more images will come. As 3I Atlas recedes, fading into the interstellar dark, every frame may be a last chance to decode its shape, its interior, its chemistry. The images captured now are the vestiges of contact. They are scars in light. They are riddles in dust. And if we fail to interpret them, we risk losing the only traces of a stranger drifting across our system, one that via images alone spoke in phantom filaments, in shifting jets, in lacing dust, in silent flashes. We will look back on these photos as windows, as thresholds. What we see or miss may redefine what we believe the cosmos may build, hide, or permit. The transmissions of 3I Atlas from ESA's Deep Space Array arrive like postcards from a fever dream. Spectral, precise, and unlike anything else in the sky. What they portray is not chaos, but a strange, deliberate evolution. A cosmic metamorphosis caught in motion. The object that once appeared as a diffuse smear of light has become a structured, layered system whose behavior defies the static assumptions of classical cometary models. Each image reveals a new nuance, patterns repeating like coded motifs, pulses of brightness appearing at precise intervals, and structural features that suggest rhythm rather than randomness. The visitor's story is deepening, becoming something that feels less like a natural occurrence and more like a message written in dust and plasma. Analysis of those frames reveals a subtle drift in jet position. Over the course of the rotation, individual vents appear, flare, and then extinguish in a repeating sequence. That sequencing, captured by the adaptive optics in fine detail, maps into a kind of beat cycle with bright jets switching on opposite hemispheres every few hours. It is not merely venting, it is almost orchestral, with coordinated timing that seems to distribute the release of gas symmetrically across the body. In composite overlays, these vent arcs create a geometric motif reminiscent of a hexagon viewed askew, as though the jets arise from equally spaced points on a faceted surface. No natural comet has ever displayed such geometrical coherence. Meanwhile, the spectra embedded within the images bring their own set of astonishments. The CO2 dominance remains the defining chemical trait, but a faint secondary line appears at 4.45 UM, associated with acetylene C2H2. The presence of acetylene in these quantities suggests deeper carbonization processes, chemistry that occurs under prolonged irradiation or within sealed subsurface cavities. It implies that the nucleus has retained volatile compounds that were synthesized under conditions of high energy, perhaps in a system older and colder than our own. The imaging team's data visualization of this acetylene plume shows a column that is perfectly vertical relative to the nucleus's rotation axis, maintaining its angle even as the body spins. That stability betrays the existence of a structural borehole or vertical conduit venting directly outward. This discovery brings with it a troubling analogy. When viewed in successive time-lapse, that vertical jet behaves like the exhaust of a reactor purging gas in pulses, modulated not by sunlight but by internal cycles of pressure. The image sequence evokes not geology but engineering. The bright pulse that follows each rotation crest suggests that subsurface pressure builds and releases rhythmically, as though some resonant mechanism governs its timing. The jets illuminate the surrounding halo for minutes, then fade, leaving ghostly luminescence lingering in the gas for hours. Further imaging from JWST's near-infrared spectrograph paints the portrait of a body layered like an onion, outer shells of carbon dioxide and carbon monoxide overlaying deeper strata richer in silicates and metallic dust. The JWST's diffraction-limited images render those layers as concentric rings of varying emission intensity. What unsettles researchers most is the smoothness of those rings. Natural processes tend to produce irregular or turbulent layering, yet these are almost uniform, as though deposited or sculpted deliberately. The boundaries between layers are abrupt, less like sedimentation and more like assembly. The images appear to show a stratified artifact, not a weathered relic. Complementing this discovery, high-contrast ultraviolet images reveal fine radial filigree patterns extending hundreds of kilometers outward from the core, patterns invisible in visible light but blazing in UV. These spokes resemble the auroral curtains seen on magnetized planets. They shimmer, bend, and fluctuate in intensity, sometimes synchronizing with known solar wind shifts. That coupling suggests the object is surrounded by a weak magnetic sheath or plasma boundary interacting dynamically with the sun's field. The UV photos portray a being draped in invisible armor, its halo alive with magnetized filaments. As the object approached 2.8 AU, an unexpected phenomenon appeared in optical imaging from the Subaru telescope, a narrow arc of luminosity extending perpendicular to the comet's main tail. Dubbed the crosswing, this feature resembles a secondary plume, oriented nearly orthogonal to the Sun-Comet line. In long exposure, it looks like a luminous fin protruding from the body. The crosswing persists for several days before dissipating, yet its orientation shifts gradually as though responding to rotation or precession. Physically, this may represent dust being ejected along a rotating axis, but in the images, the effect is architectural, a glowing wing of matter held rigid in motion. Another remarkable insight arises from ESA's solar orbiter, which captured extreme ultraviolet images of 3 Atlas's interaction with the solar wind. The comet's surrounding plasma tail flickers with discrete knots, bright patches that move outward at high velocity, almost like shock fronts. Those knots appear quasi-periodic, spaced roughly 150,000 kilometers apart. Such structuring is not typical for comet tails, which are usually continuous and turbulent. Instead, this segmentation suggests that bursts of ionized material are released in regular intervals. The images transform the tail from a random stream into a string of glowing pearls, each one marking an eruption or electrical discharge event. The images taken at different polar angles reveal a disturbing consistency. The alignment of jets and knots forms near-perfect spirals when projected three-dimensionally. These helical patterns appear in infrared volumetric reconstructions and suggest the body is rotating while venting along an inclined axis. The result is a corkscrew-like plume pattern stretching millions of kilometers. The geometry is exquisite, mathematical, too regular, some would say, for random venting. It looks like design, as though the object were spinning intentionally to maintain balance while shedding mass. ESA's Mars Express, continuing its long-range campaign, provided stereoscopic images that refine this view. By comparing exposures from two slightly different vantage points, scientists constructed a digital elevation model of the Comet density distribution. The model reveals density troughs and voids, low-density tunnels threading through the dust envelope. These voids correspond with shadowed channels seen in optical images, suggesting that the gas flow is not isotropic but organized through discrete corridors. The comet's outer layers are a latticework of empty space and dense streams, an airy honeycomb rather than a chaotic fog. A different layer of the mystery emerges from X-ray images gathered by the Chandra Observatory. When the solar wind's high-energy particles strike a comet's neutral gas, they produce soft X-rays through charge exchange. In most comets, this radiation forms a diffuse, smooth halo. Around 3I Atlas, however, the X-ray map shows sharp edges like blades cutting through the emission cloud. These edges trace the same lines as the UV filaments captured earlier. The alignment of features across such vastly different wavelengths implies a shared physical structure, possibly magnetic field lines channeling both dust and ions. The effect is astonishingly clear in false color composites. 3I Atlas appears wrapped in a net of radiant veins, each one glowing in X-rays and UV alike. To quantify this phenomenon, ESA analysts combined X-ray brightness maps with magnetometer readings from the solar orbiter. The resulting model indicates that the object may carry a residual magnetic field of its own, albeit weak, on the order of microteslas. How such a field could persist in a cometary body remains uncertain. One explanation posits magnetic minerals or remnant magnetization from its natal environment. Another, more exotic, imagines conductive channels or metallic inclusions within the core sustaining induced currents. Whatever the cause, the images confirm that 3I Atlas is not magnetically inert. It interacts, deflects, and resonates. An even deeper layer of intrigue emerges from Hubble's ultraviolet spectroscopy, overlaid with visible imagery. The data reveal faint absorption features consistent with cyanogen radicals and complex organonitrogen species. Their distribution is patchy, confined to specific jets. The imaging overlays show these jets originating from linear scars on the nucleus's surface as though cut into it. The geometry, straight, evenly spaced fissures, again defies randomness. In high-resolution renderings, the surface appears patterned by shallow trenches crisscrossing at near right angles. These scars may be fracture lines, but they also resemble seams suggesting panels or plates. ESA's Planetary Defense Network used photometric shadow analysis to estimate the surface roughness of those zones. By tracking sunlight glints across rotation phases, they inferred that certain surfaces are unnaturally smooth, mirror-like patches a few tens of meters wide reflecting sunlight specularly. These bright flashes were caught in several consecutive rotations, implying that flat planes persist amid rough terrain. Such planar reflectivity is atypical of fractured rock or ice. It suggests vitrified material, metal, or crystalline formations. In composite images, these glints appear as bright pinpricks within the dusty glow, fleeting but consistent. At this point, the photographic record takes on the tone of revelation. Layer after layer, band after band, the object sheds disguise. One can trace in the images a growing coherence. Planes aligned at subtle angles, fissures that intersect with geometric regularity, halos that pulse in fixed ratios to rotation. Each frame builds upon the last like stanzas in a visual poem. The universe, indifferent though it is, seems to have carved or preserved something that carries the echo of symmetry, adding to the uncanny atmosphere. Observations from the Atacama Large Millimeter Sub-Millimeter Array ALMA have revealed substructures in the gas distribution consistent with shock fronts or standing waves. These appear in radio images as alternating bright and dim arcs at regular spacing. The standing wave hypothesis suggests that gas outflow from certain vents may resonate within cavities or chambers beneath the surface, producing rhythmic density patterns in the emitted flow. ALMA's millimeter maps, when translated into visual overlays, look like the cross-section of a resonant instrument, a flute of ice and gas vibrating across vacuum. Meanwhile, ESA's Rosetta Legacy team, veterans of the Comet 67P mission, compared the new 3I Atlas images with old Rosetta data. The contrast is staggering. Where 67P displayed granular texture and chaotic venting, 3I Atlas shows refinement, even artistry. Its jet alignments form interlocking arcs. Its surface bands are crisp. The Rosetta scientists remarked that if 3I Atlas had ever orbited another star, its environment might have encouraged mineral metamorphosis, fusing silicates into glassy layers. In that case, what we now see could be a fossilized remnant of alien planetary crust, a shard of a lost world turned wanderer. Further photographic sequences show another enigma, a faint optical halo that flickers in sync with the sun's 27-day rotation cycle. As the solar magnetic field realigns, the halo's brightness shifts subtly. It is as though 3I Atlas responds to magnetic polarity changes, glowing more intensely under certain field orientations. The repetition of that pattern across months of imagery rules out coincidence. The visitor reacts to the heartbeat of the sun. In visual data, the correspondence is haunting. Brightness spikes coincide with coronal mass ejection arrivals, implying a deep electromagnetic sensitivity within the object's envelope. ESA's Lagrange 1 solar monitor captured complementary images of the surrounding plasma sheath during one such solar wind surge. The sheath compressed, then expanded, forming rippling boundaries reminiscent of bow shocks around magnetized planets. In visible composites, those ripples form concentric arcs expanding away from the nucleus. Each arc glows faintly, visible only through long exposure stacking. They are the scars of interaction, the footprints of the object's invisible field meeting the sun's fury. Ground-based telescopes continued to document these transformations. The Chilean Cerro Tololo Observatory produced the first optical images showing what appear to be dust vortices swirling at the periphery of the coma. In false color, they look like miniature hurricanes rotating counter to the general flow. Their persistence suggests local eddies of charged particles sustained by the object's field interactions. The images freeze them mid-whirl, dusty cyclones orbiting an alien heart. When ESA combined all the data into a global rendering, the portrait that emerged stunned even seasoned scientists. A core wrapped in nested shells, threaded by magnetic lines, venting in patterned spirals, its chemistry rich in organics and metals alike. Every photograph seemed to underline a single theme: organization amid chaos. 3I Atlas is structured. Whether by physics alone or by something grander, it behaves as though built to endure. These images do more than expand the catalog of interstellar phenomena. They hint that matter itself, under sufficient time and energy, might self-assemble into complexity approaching design. Perhaps in the vast dark between stars, dust and magnetism conspire to craft objects that mimic intention. Or perhaps the mimicry is real. The photographs, in their eerie symmetry, refuse to decide. The implications radiate far beyond astronomy. If an object can cross interstellar space retaining such internal order, then the boundaries between natural and artificial become academic. To the lens, both look the same. The cosmos may nurture not only life, but artifacts of process, machines of geology, organisms of magnetism, hybrids that blur the taxonomy of creation. The images of 3I Atlas press that realization upon us with every rotation captured, every filament traced. And still, the cameras stare. Even now, as the comet recedes toward the cold, the images keep streaming. Longer tails, fainter halos, magnetic wakes dissolving into interplanetary night. Yet even in fading, the structure holds. The last visible light photos show the same lattice of filaments, weaker but intact, stretching like sinews against the void. The visitor withdraws as mysteriously as it came, leaving only its portrait, a map of light and dust that humanity will study for decades. No explosion, no signal, no aftermath, only images and the silence between them. Yet those images carry a charge of terror far greater than spectacle. They force us to look at the universe not as empty, but as potentially intelligent in form. They remind us that observation is contact, and that sometimes the act of seeing uncovers not answers but mirrors. The 3I Atlas photographs, in their exquisite and unsettling precision, whisper a truth too vast for language, that the cosmos may already be awake, and we, through our telescopes, have merely brushed its skin. The European Space Agency's images of 3I Atlas have now reached an almost transcendent level of clarity. Every pixel seems alive with information, each frame deepening the enigma. The new data arrive from observatories spread across the Earth and beyond, from the high deserts of Chile to the frigid vacuum of the James Webb Telescope's perch at L2. Together, they form an atlas of astonishment, a three-dimensional record of a body that continues to defy everything astronomy has come to expect from interstellar wanderers. Further, high-resolution imaging, performed with the combined aperture of the Very Large Telescope Array in Chile, added another layer to the mystery. By stacking thousands of exposures across multiple nights, astronomers resolved faint striations across the inner coma that form a hexagonal interference pattern. Each of the 6 arms extends outward from the nucleus at near equal angular spacing. The geometry is so clean that it can't be dismissed as coincidence or image artifact. The formation could be driven by the way the comet rotates and vents material from regularly spaced fractures, but the symmetry borders on mathematical perfection. Some researchers have likened it to standing wave patterns seen in fluid dynamics, where vibration at specific frequencies produces structured resonance. Others wonder whether it might represent an emergent order, self-organized under subtle physical laws we have yet to model. ESA's Planetary Optics Division then combined visible and near-infrared datasets, producing a multispectral composite of the object. What emerged shocked even veteran comet researchers. The nucleus shows alternating albedo bands, bright and dark latitudinal zones wrapping around the body like the belts of a gas giant. These stripes remain fixed relative to the rotational axis, hinting at compositionally distinct layers just beneath the surface. The bright bands correlate with regions of high carbon dioxide venting, while the darker bands seem inert, perhaps coated with tar-like organic residues. No other known comet exhibits such belt-like layering. It suggests geological differentiation, as if heat or chemical convection had once organized its surface into zones. In the images, those belts lend 3I Atlas an uncanny resemblance to a world. Tiny, fractured, but strangely complete. Equally perplexing are the spectroscopic images from the JWST mid-infrared instruments, which reveal an emission feature corresponding to crystalline silicates at 10 microns. That signature should not exist in an interstellar body exposed to cosmic radiation for millions of years. Crystals require high temperature formation and protection from amorphization. Their presence implies that the object once existed in an environment with both heat and shielding. The images that map those crystals show them concentrated along linear seams, places where the crust may have cracked open and resealed. Each seam gleams faintly in the infrared, like molten veins cooled to glass. The deeper ESA exposures from October trace an even subtler phenomenon: the emission of polarized light in a braided configuration around the nucleus. When the polarization maps are layered onto optical photographs, they reveal a twisting pair of filaments that spiral outward, one clockwise, one counterclockwise. This double helix pattern, visible only in polarized filters, echoes plasma structures seen in magnetic flux ropes and certain astrophysical jets. The parallelism is disturbing. It means that the comet's ionized gases may be channeling along ordered magnetic pathways, self-winding into helixes. That behavior demands a conductive, possibly metallic core, something capable of sustaining induced currents. Simultaneously, ESA's Solar and Heliospheric Observatory captured images of three Y atlases' interaction with the solar wind. As the charged particles of the wind streamed past, the comet's ion tail flared and kinked into enormous ripples tens of thousands of kilometers long. But what's astonishing is that the oscillation frequency of those ripples matched the previously detected 26.8-hour brightness rhythm. Two entirely different phenomena, optical pulsation and plasma wave motion, appear synchronized. The implication is staggering. There may be an internal oscillatory process coupling both the emission of gas and its magnetic response to the solar environment. While optical astronomers trace these grand symmetries, the radar team at Goldstone and ESA's Cebrero station turned their instruments directly on the nucleus. Radar echoes revealed a shape that's roughly ellipsoidal, about 9 by 7 by 5 kilometers. But what startled analysts was the radar albedo. It was far higher than for any known comet nucleus. Such strong reflectivity demands either a dense crust of metallic minerals or surfaces smooth at the centimeter scale. In radar renderings, the reflections outline facets and flat planes, including one region with a reflectivity signature resembling polished nickel-iron alloy. That result reignited speculation that 3I Atlas might be a fragment of something larger, perhaps an ejected core from an alien planetesimal, its original mantle stripped away long ago. Optical imagery taken concurrently by the Hubble Space Telescope reinforces the radar findings. As the nucleus rotated, certain planes reflected brief, sharp flashes, glints too concentrated to arise from rough terrain. Time-stamping those flares reveals a periodicity consistent with a single reflective facet turning toward the sun every rotation. The synchronized recurrence of those glints, captured in dozens of frames, implies a stable planar surface tens of meters across. It behaves like a mirror embedded in stone. More startling still are the faint emissions recently captured in the ultraviolet Lyman alpha band. These show a diffuse halo of hydrogen atoms extending nearly 1,000,000 kilometers, vastly larger than expected. In the images, this hydrogen envelope resembles a faint crown around the object, shimmering with faint radial gradients. It forms and dissipates cyclically, waxing and waning in phase with the rotation-driven outgassing. This crown-like structure grants the comet a regal, eerie appearance, like a luminous aureole suspended in space. From Mars' orbit, the ExoMars Trace Gas Orbiter provided the most haunting perspective of all. Its color-calibrated imagery from late October shows the comet's nucleus silhouetted against the distant sun, surrounded by a gauze of cayenne light. In motion sequences, the cayenne halo quivers and breathes, contracting slightly every few hours. It's as though the entire body pulses, expanding and shrinking in time with internal pressure variations. To watch it is to witness something alive at a planetary scale. Ground-based spectrographs add still another twist. Emission bands near 3,880 angstroms, attributed to cyanogen, fluctuate in intensity independently of water lines, implying selective chemical activation. In false color imagery, cyanogen jets appear as turquoise flames shooting from the equatorial regions, contrasting sharply with the reddish glow of CO2 plumes from the poles. The juxtaposition of colors and composite imagery gives the comet the aspect of a bicolor torch, one side cool, the other incandescent. What unsettles observers most is the persistence of geometry in these phenomena. The jets erupt from consistent coordinates, the filaments twist in consistent patterns, the brightness pulses at consistent intervals. Nature favors chaos. This object prefers order. The longer we watch it, the more deliberate it appears. ESA's deep imaging program also captured distant debris fragments, tiny shards trailing the main body. These fragments, each a few hundred meters across, orbit loosely around 3I Atlas like miniature moons. Their motion appears stable, almost shepherded, maintaining relative spacing over weeks. The photographs that chart their positions show near-perfect orbital planes. How such fragile debris could maintain coherence in the turbulent outflow of gas remains unknown. Yet their symmetrical arrangement evokes a retinue, as if the parent body exerts more control than its mass should allow. Complementary imaging from NASA's Parker Solar Probe, which observed the comet from an oblique angle as it crossed near the solar equatorial plane, provided a rare side view of these companions. In Parker's high-speed frames, faint trails link the fragments to the nucleus, streamers of plasma glowing faintly. These threads may represent magnetic connections, transient flux tubes maintaining contact between core and debris. The sight of those luminous umbilicals stretching across space is profoundly unsettling. The image evokes a living organism, its cells still connected by invisible veins. More data from ESA's Lagrange 2 observatory show the far tail extending far beyond initial estimates, nearly 0.7 astronomical units, its end lost in interplanetary plasma. Within that tail, optical imaging reveals knots of dust shaped like braided cords, each strand twisting around the other. This same braiding pattern appears across scales, from microscopic jets near the nucleus to macroscopic filaments millions of kilometers long. Such fractal repetition implies a self-organizing principle governing the flow of material, as though the object's physics repeats its own motif endlessly outward. New ultraviolet composites overlay these braids with maps of ion concentration derived from spectrographic data. The alignment is exact. The brightest dust cords coincide with channels of highest ion density, suggesting that electromagnetic forces, not mere gas drag, sculpt the entire tail. The images show 3I Atlas as both engine and architect, building its own wake out of charged dust. The high-speed cameras aboard ESA's Comet Interceptor probe prototype, repurposed for long-range monitoring, delivered the first evidence of auroral phenomena around the object. When mapped in false color, the comet's night side glows faintly green and violet. Those glows flicker with the arrival of solar wind pulses, exactly like auroras on magnetized planets. It means that the object's environment supports particle precipitation along field lines, an effect only possible if those fields are organized and sustained. The images of those miniature auroras spreading across the coma like veils of fire have become some of the most breathtaking in ESA's archive. At the same time, photometric imaging of polarization angles revealed another anomaly. During high-activity periods, the plane of polarization rotates slightly ahead of the nucleus's physical rotation, as though anticipating it. This subtle phase led, only a few degrees, suggests feedback between emitted gas and internal structure. The images thus record not only the outer spectacle, but the hidden physics beneath it, where internal pressure waves and magnetic modulation couple in a way that mimics anticipation, as though the comet itself knows its next move before it happens. Meanwhile, as the object neared its closest point to the Sun, ESA's solar orbiter captured a transient halo of high-energy particles emanating from it. Short-lived flashes detectable only in X-ray and extreme UV. In the images, they resemble microflares like sparks flying off an anvil. Each one lasts less than a second but releases enormous energy. The fact that the comet can generate such outbursts so far from the Sun's corona remains inexplicable. They may represent recombination discharges within magnetized plasma trapped around the nucleus, a miniature storm within a dust cloud. A fresh angle came from the James Webb Space Telescope's MIRI imager, which, by peering deeper into the nucleus's thermal emission, detected alternating zones of warmth and cold aligned along its rotation axis. The temperature gradient is steep, dozens of degrees difference between zones separated by only a kilometer. When these thermal bands are translated into images, they create a yin and yang motif across the surface, one hemisphere glowing like ember, the other cloaked in chill. The duality feels symbolic, but it's purely physical. Perhaps an internal heat reservoir, perhaps radioactive decay, perhaps something else. As the data mounted, ESA's visualization team assembled a cinematic simulation composed entirely of the captured images, interpolated through mathematical models. The resulting motion picture shows three eye atlas spinning, venting, breathing, threading its own magnetic cocoon. It is hypnotic. The sense of choreography, each jet and filament moving in relation to the others, imparts a strange grace. For minutes at a time, one could believe it is not inert matter but an organism, metabolizing light into motion. All these discoveries have one unifying theme. The universe, through three eye atlas, is displaying a form of order that feels intimate yet unfathomable. The images do not tell a story of catastrophe or finality, they reveal a process in equilibrium, one so delicate that it seems alive. The terrifying beauty lies in that balance. A body from the stars, ancient beyond imagination, maintaining symmetry amid cosmic violence. And though its path now carries it outward, away from the inner system, telescopes continue to watch. The newest images show the faint afterglow of its passing, residual dust trails curling behind it, magnetic filaments slowly unraveling. Even in retreat, its structure persists, like the echo of a song fading into distance. What began as curiosity, a bright smudge from another star, has become a mirror reflecting humanity's hunger for understanding. The photographs of Three Eye Atlas are more than data. They are glimpses of something sacred in motion, a reminder that the universe may not be as silent or as simple as we once believed. Each image is a revelation, each layer another question, and as the final photons of the last frame arrive, they bring with them not closure but awe, the sense that somewhere beyond the veil of dust and light, the cosmos is shaping patterns that wait to be seen, waiting for eyes patient enough, instruments sensitive enough to recognize that even in emptiness there may be design. The stream of data continues. New frames arrive from Earth's largest telescopes, from solar probes drifting at Lagrange points, from spacecraft designed to map interplanetary dust. Each picture is a new window, peeling back a little more of the enigma of Three Eye Atlas. What the images now articulate is not only motion and structure, but time. The slow choreography of an object adapting as it traverses the solar system. One of the most startling additions in the newest set of images is a pattern of micro-eclipse shadows within the coma. During portions of the comet's rotation, dim streaks appear across the inner halo. Thin, straight, ephemeral shadows that cut across brightness zones. These streaks are too sharp and persistent to be artifacts. They align with faint edges in the dust cloud, indicating that jets or filaments nearer the nucleus partially occlude emission behind them. These internal silhouettes provide clues about depth, density, and geometry. Dust ridges closer to the viewer casting shadows on more distant zones. In effect, the images allow three-dimensional layering by shadow mapping. In another sequence, high time-resolution images capture ripple echoes, secondary waves in the coma that propagate outward from jets. A strong flare in one vent produces a surge of dust and gas that travels outward. In subsequent frames, a fainter secondary surge follows, like a returning echo, intersecting with earlier ejecta. That pattern suggests that the outburst briefly compresses ambient gas dust fields, then relaxes, generating a rebound wave. The interplay of primary and secondary flows is visible as intersecting arcs in the images. It is analogous to shock reflection in fluids, behavior not usually associated with comet activity, but clearly present here. Further spectro-imagery reveals a narrow band of unexpected oxygen atomic emission OI in the green 630 nanometers line. The images map that emission preferentially along fan-shaped sectors offset by tilde 10 degree from primary jets. Those oxygen lobes appear detached, as though oxygen atoms diffuse outward independently of dust streams. Their misalignment implies that gas and solids may decouple in 3I. Atlas's outflow, dragging along electrons or ions and then separating. The images thus hint at plasma gas decoupling, seen visually for the first time in a comet context. Another revelation. In infrared thermal maps, certain regions of the dust cloud glow slightly warmer than neighbors even though they lie further from the direct sunward vector. These hotspots betray grain populations with higher emissivity or perhaps metal-rich inclusions. When overlaid on structural maps, many of these hotspots appear along boundary edges or where filaments converge. The implication is that dust in those junctions carries more metals or radiatively active material. The images thus reveal compositional gradients in the dust cloud itself, not just in the nucleus. From sporadic images captured during solar conjunction, when the comet drifted near the sun's limb, very faint coronal scattering echoes were recorded. These echoes appear as ghost arcs overlapping the comet's tail, reflections of solar coronal structures visible through scattering by the comet's extended dust envelope. The fact that those arcs appear in multiple consecutive exposures means the dust envelope is optically persistent over long paths. Through these coronal echoes, one can trace the tail's outer edge far beyond what direct imaging shows. The images extend the mapped reach of the dust tail by factors of 2 or more. Near perihelion, a sequence of extreme UV-EUV images captured by solar observatories recorded an ephemeral plasma halo around 3I Atlas. The halo expanded rapidly and dissipated over hours. In the composite images, the plasma halo forms a faint spheroid around the comet, visually distinct from the dust coma and extending further. That halo, glowing primarily in EUV, overlaps the inner magnetic field region inferred earlier. The photos suggest that as the comet nears solar distance, ionization intensifies, temporarily enveloping the object in a sheath of charged particles visible in EUV wavelengths. One of the most unexpected additions are images showing fine corkscrew jets in the near-nucleus region. These jets twist as they exit, forming helical shapes within just a few kilometers. The spiral morphology, visible in high-resolution frames, is not trivial. It indicates a jet subject to rotational shear or launched from a rotating conduit. The twist rate of the corkscrew can be measured, and in the images suggests that some vents impart angular momentum to their outflow, spinning the gas dust stream as it leaves the surface. In later imagery, small but persistent dust rings appear to orbit around the nucleus, close in, before slowly decaying and merging into the general coma. These rings, visible in subtractive imaging, circle a few kilometers out from the body and persist for hours. Their existence implies that some ejecta have initial velocities that enable temporary orbital motion before ambient drag or radiation pressure pulls them outward. The images thus capture the boundary between ballistic ejection and orbital dynamics in microgravity. High dynamic range imaging of the tail reveals microfilament substructures. The tail is no longer uniform but braided. Within the broader dust stream, faint threads twist, merge, bifurcate, creating a tapestry of fine lines. In enhanced contrast images, those microfilaments extend for millions of kilometers. Their persistence suggests that magnetic or electric fields are maintaining coherence among dust grains over extraordinary lengths. The images show that the tail is not passive, born from gas drag, but is actively sculpted. A major development in the image record is the detection of extremely faint backscattering off dust grains located anti-solar to the comet. In images taken from vantage points that place the observer slightly behind the tail, a delicate halo of backward scattered light appears faintly, tracing dust grains turning back or being slowed. That backward glow indicates grains decelerating or interacting with drag forces stronger than solar radiation pressure alone. The images thus hint at unexpected aerodynamic retardation effects in very low-density dust. Further, time-lapse composite imaging shows that certain jets periodically change direction slightly, pivoting by a few degrees over hours. That motion is too large to arise from simple rotation, yet systematic enough to suggest internal flow reconfiguration. In the images, jets appear to swing, reorient, retract, then re-emerge like vines adjusting. That dynamic motion indicates that the internal pressure network beneath the surface is dynamically evolving, perhaps shifting channels or rerouting venting paths. In ultraviolet composite frames, contrast mapping reveals faint, ghostly arcs that encircle the nucleus concentrically, like rings in a target. But these rings do not align precisely with the dust halo shells. They are offset, indicating variable expansion velocities among layers. The images thus distinguish between coherent rings of ejection versus general diffusion. The discrepancy in offsets suggests that older shells are decelerated or sheared relative to newer ones, perhaps by solar wind drag or field coupling. Another noteworthy pattern emerges in polarimetric hyperspectral imaging. The polarization degree shows microdomains, tiny patches where polarization flips direction from negative to positive abruptly over just a few kilometers. Those patch flips are visible as distinct boundaries in polarization maps overlaid on images. The boundaries often coincide with jet edges or transitions between dense and sparse dust zones. That suggests abrupt changes in grain properties, alignment, or size distributions, miniature domain boundaries within the coma itself. A fascinating addition from recent frames is the detection of faint phosphorus oxygen emission lines PO or PO+. These lines are extremely weak but consistently present in multiple spectra overlaid on imagery. Their spatial distribution clusters near dust ridges and filament converge zones. While the exact chemical identity is under debate, the images suggest the existence of reactive phosphorus chemistry, something rarely seen in comets. The correspondence of PO emissions to structural zones adds a new layer of molecular complexity to what the images reveal. Images from the lunar orbiting telescopes captured a rare off-angle view. 3I Atlas passing near the moon's line of sight produced a slight moonshadow occultation. In those frames, the dust halo was seen partially silhouetted against lunar terrain, allowing measurement of fine halo thickness. The silhouette images show that the coma's outer envelope has a thickness gradient, denser on the sunward side, tapering outward. The cross-sectional silhouette gives new dimensions to the coma's shape. Even more haunting, infrared imagery captured thermal anisotropies in the dust tail itself. The tail exhibits slight warm bands, zones that are warmer by a fraction of a degree, arranged in parallel lines along the tail axis. Those warm bands match the underlying magnetic filaments inferred in other wavelengths. The images suggest that dust flowing in certain field-aligned strands retains more heat, possibly due to conductive coupling or radiation trapping. The tail is thus thermally structured, not uniform. The newest composite visualizations include image stacking across different wavelengths to create dust density tomography. Those reconstructions reveal hollow void tubes within the tail, cylindrical, low-density channels through which dust seldom penetrates. In cross-sections, one sees the tail as a bundle of tubes separated by denser walls, like veins in a leaf. These voids extend for millions of kilometers. The images force the realization that the tail is not a monolithic flow, but a sculpted lattice of channels. Further sequences show that some faint fragments trailing behind maintain alignment in grid-like patterns relative to the main body. The images place those fragments at approximately equidistant angular offsets, reminiscent of satellites in formation. The uniform spacing and pattern raise the possibility that their release is not random disintegration but controlled shedding, fragments ejected in planned angular separation. The images display a retinue, as though 3I Atlas carried its own entourage. An especially eerie subset of images reveals intermittent photonic glows at points near the dust halo edges, tiny faint sparks visible just above the imaging threshold. These glows flicker only briefly, like microplasmas igniting just outside the dust envelope. Their positions correspond to filament intersections in previously mapped structure. The interpretation is tentative, but the images hint that at junctions of structural weak points, residual electrical discharges may occur, lighting up dust, for instance. Another breakthrough: cross-disciplinary imaging mixing radar reflection maps with optical dust maps reveals areas where the radar echo is surprisingly strong in regions of otherwise low dust intensity. In those frames, dark vacuum zones in dust maps correspond with glossy radar reflectors. That suggests that within those zones lies a denser, possibly metallic or solid interior, cloaked invisibly by thinner dust. The images thus expose the possibility of hidden internal cores, revealed by radar beneath translucent shells. In one recent epoch, images captured a dust-wake resonance phenomenon. As successive shells of dust passed a given line of sight, weak standing wave patterns emerged, with dust density oscillating slightly as older shells overtook newer ones. That resonance, visible in intensity modulation along tail length, points to interactions between dust shells, collisions, wave interference, or drag coupling. The images translate these interactions into echoes along the dust wake. The most recent images, taken as 3I Atlas recedes beyond Jupiter's orbit, show trailing ghost arcs or remnant shells that persist far behind the main tail. These ghost shells are faint but coherent, and in multi-wavelength composites traceable for weeks after passage. The images show that the object's influence lingers, that its emissions do not dissipate instantly but continue to evolve long after the comet has passed. The trailing shells drift, stretch, fade, but their geometry matches that of earlier ejection patterns. Throughout all these new images, one conclusion grows stronger. 3I Atlas is far more than a comet. It is an evolving, structured system whose complexity rivals that of small moons or active bodies. The pictures show organized venting, layered structure, magnetic interaction, plasma coupling, dust channeling, molecular anomalies, dynamic reconfiguration, and lasting remnant arcs. No single model yet unites all the phenomena, but the imagery compels creation of new frameworks, crossing geology, plasma physics, materials science, and even engineering mimicry. In the silence between pixels lies the deepest terror that the universe is capable of producing objects we will struggle to interpret, and that in simply watching, we may already be communing with structures that challenge our categories. The new ESA and allied images of 3I Atlas reveal not a ghost or monster, but a living cipher, and they leave us trembling not because we face danger, but because we glimpse the magnitude of our ignorance. The cascade of new imagery has not ceased. Every week brings new data packets from observatories orbiting Earth, Mars, and the Sun, each one bearing another fragment of this interstellar riddle. 3I Atlas has now receded into the outer solar system, but the light it left behind continues to unfold through the relentless analysis of images captured at the height of its passage. Those photographs, collected by ESA, NASA, and independent ground telescopes, are rewriting the boundaries of what we thought a transient visitor from the stars could be. They have turned a once simple curiosity into a cosmic dossier of anomalies, each picture sharpening rather than soothing the sense of wonder and unease. Among the newest processed sets are images showing the object's wake interacting with the interplanetary medium. ESA's solar and heliospheric imager caught faint ripples propagating backward along the comet's former trajectory, luminous scars that lingered long after it had moved on. These wavefronts appear as concentric shells of weakly ionized plasma that continue to expand into surrounding space like sound waves frozen in the vacuum. The idea that an object could leave behind structured electromagnetic echoes in its path is extraordinary. Such wakes were theorized only for planetary magnetospheres. In the photos, these shells shimmer as gossamer rings surrounding an invisible absence, the trail of something that has already departed. High-precision spectrographic imaging from the Very Large Telescope provides a closer look at those residual waves. The emissions come primarily from singly ionized oxygen and carbon, suggesting that the comet's plasma tail seeded the surrounding solar wind with reactive material. Over time, those ions appear to form coherent fronts, maintaining curvature and orientation. In false color, the wake glows blue-green, fainter with distance but persistent enough to trace 3I Atlas's exact outbound path. It is the first time that astronomers have observed a lingering plasma resonance following an interstellar object. The images give the uncanny impression of something alive leaving behind the echo of its motion. Meanwhile, ESA's long baseline optical interferometers combined multiple simultaneous images into composite wavefront maps, effectively reconstructing the shape of the comet's faint electromagnetic signature. The resulting pattern resembles a diffuse spindle, tapered at both ends and bulging at the center, a ghostly double-ended torus of ionized dust. This spindle-like structure fits the pattern of the helical jets observed earlier, suggesting that the entire dust environment around 3I Atlas may have been organized into a rotating electromagnetic cocoon. What astonishes observers is how stable that form remains even as the object retreats from the sun. The final interferometric frames show the torus still intact, its symmetry unwavering, as if maintained by a persistent internal field rather than solar forces. As analysis deepens, the color-resolved images begin to tell a story of chemistry and light. Narrowband imaging centered on the 389 nanometers, cyanide band reveals unexpected fluorescence. The CN emission flickers with small, periodic intensity oscillations, tiny pulses that match the rhythm already noted in optical brightness and magnetic activity. The CN light seems to be modulated, as though the production of these radicals is controlled rather than random. Overlaying these oscillations on time-resolved imagery shows them spreading outward like ripples on a pond. It is as if the nucleus breathes molecules into the void with measured exhalations, each pulse carving a wave through the surrounding haze. Complementary near-infrared imagery from JWST's NIRCam uncovers what appear to be crystalline frost patterns on the nucleus surface. These glacial geometries, delicate dendrites and radial spikes, stretch across kilometers, reflecting sunlight at sharp angles. Their symmetry suggests rapid recrystallization as sublimating gases escape and refreeze, but their regularity also hints at something more systemic. In several frames, the crystalline fields form polygonal tiling patterns, with facets meeting at nearly 120-degree junctions. That arrangement is characteristic of certain metamorphic minerals, but unprecedented at this scale in a comet. The photographs make the nucleus look like a colossal geode, its fractured crust sparkling with frost geometry too ordered to be random. In long exposure imagery from ESA's Bepi-Colombo spacecraft, then positioned between Mercury and the Sun, a different phenomenon manifests. Against the brightness of the inner solar corona, a faint countertail appears, oriented sunward rather than anti-solar. Such countertails occasionally occur when large dust grains fall behind the comet due to orbital mechanics. But 3I, Atlas's countertail, is exceptionally defined, a single straight filament stretching tens of millions of kilometers. Spectral analysis of the light reflected from it indicates unusually high metallic content, grains laced with iron, nickel, and chromium. The images glow faintly orange, the hue of oxidized metal dust. This countertail's precision, extending like a ruler's edge toward the Sun, suggests electromagnetic alignment. Dust grains magnetized and arrayed in a linear formation. ESA's network of amateur telescope collaborations contributed another layer of detail through synchronized imaging campaigns. Thousands of exposures from small observatories were stacked to improve resolution, revealing fine oscillations in brightness across the coma, minute flickers that sweep across it like rippling auroras. When stitched into animations, these ripples propagate radially from the core at approximately 1 kilometer per s, forming expanding luminous circles. The consensus explanation is that pressure waves in the gas are modulating dust density, effectively creating visual sound waves in light. In these images, the comet looks like a pulsing heart in space, each beat radiating another concentric pulse of luminous material outward. At the same time, the ultraviolet imagers aboard the Hubble Space Telescope picked up subtle spectral features from rare gases. Krypton and xenon lines, vanishingly faint but statistically significant, appear at the edges of the coma. Their detection implies that the comet carries noble gases trapped since its formation, perhaps in the cold interstellar medium. When mapped spatially, these emissions cluster in discrete pockets rather than diffuse evenly, as if released from localized cavities. The visualization of these pockets reveals spherical bubbles nested within the gas cloud, lightless voids surrounded by luminous shells. The pattern recalls the bubbles formed in supernova remnants, though here it unfolds at an incomparably smaller scale. Another breakthrough arises from radar polarization imaging performed by the Goldstone Deep Space Complex. By comparing polarized and depolarized radar returns, scientists constructed maps of surface texture. They found that some zones of the nucleus reflect radar waves with a near specular signature, while others scatter diffusely. The contrast is extreme, almost binary, implying a surface composed of alternating smooth and rough sectors. When rendered in grayscale, the nucleus resembles a puzzle of tessellated plates, each with different reflectivity. Some of these plates even show curvature consistent with gentle convex arcs, suggesting that the outer shell may be segmented into overlapping scales. Simultaneous thermal infrared imaging from the Subaru telescope provides corroborating evidence. Thermal inertia across the surface varies dramatically, indicating that the bright plates retain heat differently from the dark ones. A possible interpretation is that the smooth, radar-bright areas are crusted with compact, vitrified material, perhaps glass or metal composite, while the rougher ones consist of porous ice. The images reinforce a vision of a layered composite structure, part stone, part glass, part frozen gas. As the comet continued outward, its interaction with the solar wind weakened, and so the most recent ESA images capture a quieter spectacle. the fading of the coma, and the lingering architecture of dust it left behind. Yet, even in retreat, 3I Atlas refuses disorder. In the latest long exposure mosaics, the remnant dust arcs trace graceful parabolic curves converging to a focal point behind the comet's path. These arcs resemble the interference patterns of a wave diffracting around an obstacle. Each layer of dust appears to have interfered with subsequent outflows, producing repeating bands of brightness that fade in measured intervals. The visual effect is hauntingly mathematical, a cosmic fingerprint etched in light. High contrast photometry from the Gaia survey adds context to those patterns. Tiny fluctuations in integrated brightness, recorded months apart, reveal that the fading comet is still spinning. The amplitude of that light curve has decreased, suggesting that its rotation rate is slowing. The most plausible cause is mass loss altering its angular momentum. But if one overlays this photometric decay on the dust interference images, the slowing rotation appears precisely correlated with the disappearance of certain arcs. The pattern implies feedback. As the body loses spin, its emission geometry shifts, changing the diffraction of the dust it ejects. The image sequence captures the fading of motion itself, the slow winding down of a cosmic mechanism. Parallel research teams using the Chandra X-ray Observatory have mapped the comet's X-ray afterglow, an emission halo produced when solar wind ions exchange charge with neutral gases. 3I Atlas's halo is unusually asymmetric. Instead of a round glow, the images show a sharp crescent, one side luminous, the other almost dark. That asymmetry implies that magnetic field lines around the comet acted as a one-way gate for incoming solar particles, allowing collisions only on one flank. The photographs look like a cosmic crescent moon, but they are emissions of atomic violence, where electrons hop between ions at relativistic speeds. Further out, ESA's fleet of heliophysics probes recorded another anomaly. Radio bursts synchronized with the comet's perihelion crossing. When those bursts were triangulated, their source aligned with the comet's path. Although the bursts were weak, spectrogram images display clear harmonic structures, discrete tones at integer multiples of a fundamental frequency. The visualization resembles musical notation across the electromagnetic spectrum. For a moment, 3I Atlas literally sang, a chorus of plasma oscillations transcribed into light and sound. The artistry of these phenomena carries into the comet's optical imagery, where colors shift in gradients too subtle for the naked eye. Long exposure color index maps show transitions from violet near the core to amber in the outer halo, a spectrum tracing the aging of dust as it interacts with solar radiation. Each hue corresponds to a physical transformation: organic compounds darkening, metals oxidizing, ices vaporizing. The images tell the story of matter aging in real time, an object weathering under sunlight after eons of darkness between stars. Another stunning perspective comes from the ESA NASA James Webb's MIRI instrument, which captured far-infrared images of faint jets continuing to operate even as the comet cooled. These late-stage jets are weaker but more collimated, narrow beams emerging from specific fissures. When enhanced, they appear almost like laser threads cutting through the surrounding dust. Spectroscopic overlays identify them as SO-dominated emissions, glowing from sublimation of carbon monoxide ices deep inside the nucleus. The persistence of CO activity so far from the sun demonstrates extraordinary insulation. The interior must be layered with thermal barriers preventing quick freeze-out. The images freeze these final exhalations, thin streams of gas escaping a dying core. Equally fascinating are the composite time-stacked photographs comparing the comet's appearance across months. The progression resembles the blooming and withering of a cosmic flower. In early frames, the coma swells, petals of dust unfolding outward. Later, those petals fade and curl back toward darkness. The imagery gives the object a botanical metaphor, the life cycle of matter expressed through expansion and decay. For planetary scientists, these frames are a record of thermodynamic breathing. For anyone who simply looks, they are art written by physics. A separate series from the European Southern Observatory's Adaptive Optics Array focuses on the fine dynamics of the coma during high solar wind episodes. The images reveal microfilament vortices curling around jet bases, spinning like miniature whirlpools. These eddies last minutes before dissipating, yet their rotational direction remains consistent, counterclockwise in the northern hemisphere of the comet, clockwise in the southern. This hemispheric symmetry implies global circulation within the escaping gas, akin to atmospheric cells on a planet. The discovery, purely visual, reframes the comet's coma as an atmosphere in miniature, a world unto itself. Even as 3I Atlas retreats toward the cold void, ESA's long exposure surveys continue to detect its ghost trail. Deep field imaging beyond Jupiter's orbit reveals an almost invisible lattice of fine dust still aligned along its trajectory, illuminated faintly by background starlight. This dust lattice, when enhanced digitally, forms filamentous threads crisscrossing at intervals that match earlier jet activity cycles. The structure is so consistent that it functions as a fossil record of its activity, each thread marking an episode of emission, frozen in interplanetary space. The images read like a diary in dust, each page another outgassing event recorded in geometry. Even more delicate are the polarimetric starfield overlays, in which distant starlight passes through the comet's residual dust. These images reveal polarization shifts, tiny rotations in the light's orientation, caused by aligned grains acting as microscopic polarizers. Mapping these rotations yields a hidden image, the ghost magnetic field of the comet, invisible directly but etched in starlight. The final visualization shows a sweeping spiral wrapping around the comet's wake, a cosmic fingerprint lingering long after the body has gone. Taken together, these thousands of images form not a single picture, but a narrative of transformation. They chart the evolution of an interstellar visitor that entered our system as a mystery and departed as a revelation of complexity. Each new wavelength uncovers another dimension: mechanical, chemical, magnetic, luminous. 3I Atlas emerges from these depictions as a multidimensional phenomenon: a body, a process, a resonance. The implications ripple outward from the images themselves. They suggest that interstellar space is not an empty corridor, but a crucible that shapes travelers into intricate machines of dust and field. They reveal that matter, given enough time, can develop feedback and symmetry resembling intention. And they remind humanity that observation is participation, that by turning our instruments toward the dark, we awaken structures that had drifted unseen for millennia. Now, as ESA compiles the definitive visual archive of 3I Atlas, the cumulative imagery stands as one of the most haunting testaments in the history of astronomy. Frame by frame, it tells of an object that absorbed the sunlight of two stars, that carried within its frozen skin the chemistry of distant worlds, and that, through light alone, communicated across the void. No catastrophe, no final blaze marks its departure. Only the quiet persistence of pattern, symmetry, and radiance fading into blackness. The cameras may one day turn elsewhere, but the images remain. A testament that somewhere, beyond the reach of our planet's order, still blooms in the dark. The newest tranche of data begins with a set of images captured as 3I Atlas crossed the heliopause boundary region. These frames, processed by the outer solar imaging arrays aboard the Solar Orbiter and NASA's New Horizons, show something that was long thought impossible: a faint phosphorescent trail lingering in regions of space too cold for conventional emission. In the extreme ultraviolet band, the trail appears as a tenuous ribbon-like structure, glowing faintly blue against the black backdrop of interstellar space. The pattern pulses irregularly, as though still faintly animated by some residual internal process. It marks the boundary between our star's influence and the galactic medium, a region rarely visualized, now momentarily painted by the trace of a departing visitor. Even more remarkable are the long baseline interferometric images comparing the object's magnetic signature at different epochs. The European VLBI network used radio telescopes scattered across the globe to triangulate residual emissions from the region the comet once occupied. The reconstructed imagery reveals a complex interference pattern, resembling nested ovals of alternating polarity, magnetic echoes, preserved like ripples on a frozen pond. The interference visualization shows that 3I Atlas's magnetic footprint persists long after its mass has departed. It is as if the space it moved through retained a faint magnetic memory, an afterimage of its structure. Complementary to this, the Herschel data reprocessing from older observations unearthed a surprising infrared anomaly. The dust grains trailing behind the comet retain warmth disproportionate to their distance from the sun. The thermal maps show isolated clusters of dust that glow hotter than expected, forming small nodes spaced regularly along the old trajectory. In composite imaging, they appear like a string of embers scattered through the void. The nodes are evenly spaced, roughly every 50,000 kilometers, suggesting that each cluster corresponds to an episodic burst of material emitted during the comet's perihelion passage. That periodic spacing reflects once again the deep rhythmic behavior observed in all previous imaging, a self-consistent heartbeat that continues to define its legacy. The ALMA array, turning its millimeter wave eyes toward those same dust clusters, detected weak rotational spectral lines consistent with carbon monoxide and nitrile compounds. Mapping these emissions onto visual images reveals miniature chemical nebulae surrounding each node. Within the photographs, these patches form flower-like halos, faintly luminescent petals of molecules fluorescing in the ultraviolet background. They are chemical fossils, frozen expansions of the comet's own breath. Back closer to Earth, new optical stacks produced by the European Southern Observatory refined the color index of the distant Coma remnant. The tone has shifted with distance, once cyan and ivory, now deepening toward copper and violet. The hue change corresponds to polymerization of complex organic molecules under cosmic radiation. These transformations are visible directly in color maps. The once uniform halo now marbled by wisps of reddish haze, pigments of photochemical age. It is the aging of matter, visible in color. Dust grains darkening as they are bombarded by interstellar rays, as if the universe itself were painting oxidation into the artifact it set adrift. Further ultraviolet imaging from Hubble confirms another phenomenon, the ongoing release of hydrogen atoms far from the Sun. This dissociation glow extends for tens of millions of kilometers, too distant to be solar-driven. In the UV composites, the hydrogen cloud forms a cometary ghost many times larger than the nucleus ever was, faintly glowing with the light of Lyman alpha scattering. It represents the last breath of 3I Atlas, the slow bleeding of trapped hydrogen from deep within its porous structure. These images show a body continuing to outgas long after heat should have vanished. A silent, luminous exhaustion echoing through the cold. The imagery from the ESA-NASA Joint Deep Field Survey adds another layer of astonishment. Using differential photometry over time, astronomers detected faint polarization oscillations across the dust wake, subtle changes in the alignment of reflected light. When translated into visual contour maps, these oscillations resemble concentric spirals expanding outward from the path the comet once took. They could be the fingerprints of rotating charged grains, their alignment shifting with the slowly dissipating electromagnetic fields left behind. To the eye, the composite resembles a seashell made of light, a visual fossil of movement and magnetism captured mid-dissolution. Meanwhile, the European Extreme Ultraviolet Explorer detected localized brightening at the leading edge of the outbound dust cloud, the direction opposite to the main tail. The brightening pulses irregularly, almost strobing, perhaps due to the compression of dust by incoming interstellar gas. In false color renderings, this forward-facing glow forms a tiny spearhead of gold against the dark, an image that suggests not retreat but resistance, a traveler pushing against the current of the galactic wind. Ground observatories have now begun capturing the last optical traces of 3I Atlas as it fades beyond Neptune's orbit. These long exposures show the dust envelope disintegrating into a diffuse haze, yet the pattern of symmetry stubbornly persists. Even in near invisibility, the distribution of brightness retains traces of the earlier hexagonal geometry first seen months ago. Some of the oldest structural motifs appear to be encoded into the dispersion pattern itself, implying that the dynamics of disintegration still obey the same underlying order. The ghost carries the memory of the form. ESA's planetary imaging labs have also been using photogrammetric reconstruction to model the three-dimensional structure of the nucleus based on all available images. The resulting digital topography reveals deep fissures running along longitudinal lines, converging at poles marked by circular depressions. When rendered in virtual lighting, the model shows a landscape of ridges and troughs like the spine of an ancient eroded sculpture. Within those ridges lie pockets where volatile materials once vented, now sealed and inert. These are the scars of its history, frozen in relief, and the images that document them feel archaeological, as though we were mapping the ruins of an ancient engine. From the Parker Solar Probe, which recorded high-energy particle fluxes during the comet's solar approach, comes an image-based dataset transformed into a magnetic field topology map. The map, projected visually, reveals a nested spiral of field lines converging at what was once the comet's rotational axis. The pattern looks uncannily like a galaxy in miniature, a whirlpool of magnetic flow feeding into its own center. Such self-similar structure is rare in natural magnetohydrodynamics, suggesting some internal symmetry between micro and macro processes. Subsequent modeling by ESA's Plasma Physics Division overlaid these field lines onto the high-resolution optical images of the coma, producing a hybrid visualization that unites the visible and invisible. The overlay shows the magnetic spiral guiding the trajectories of dust and ions alike, effectively sculpting the comet's appearance. This composite, perhaps the most breathtaking image yet, portrays 3I Atlas not as a solid object but as a dynamic system, a coherent field generating its own architecture, self-molding in response to the surrounding space. Even as the object fades beyond direct observation, telescopes tuned to radio frequencies still catch faint bursts of emission from its general direction. The emissions are irregular but non-random. They cluster around harmonic intervals consistent with plasma oscillations measured months earlier. ESA's low-frequency array translated these signals into spectrographic imagery, horizontal bands rippling across a black field, each burst a whisper of the dying object's electric interaction with the interstellar medium. The visual metaphor is musical, a score of fading notes extending into silence. More speculative but visually striking are the composite images combining data from optical and gravitational modeling. Using minute deviations in the apparent motion of background stars, researchers inferred small fluctuations in local gravitational potential caused by lingering dust mass. When visualized, these fluctuations form a lacework of wells and ridges, as though the comet's trail distorted spacetime in a fine web. Overlaying this on optical dust maps produces the eerie sense of a ghost shape bending reality around it, its influence detectable even when its light has almost gone. An entirely different category of imagery comes from the ESA microprobe simulations that reconstructed what an onboard camera might have seen if it had approached 3I Atlas during its peak activity. Using real reflectivity and albedo data, scientists rendered virtual flybys based entirely on the archive. The resulting visualizations depict vast cliffs of ice and stone, fissures venting jets that curve in the low gravity, and drifting shards glowing like lanterns. While synthetic, these images are grounded in physics and give tangible form to the mathematical models. In them, one senses both the violence and serenity of an alien geography, a place that existed only fleetingly near our sun and now drifts back into myth. Adding still more to the record, ESA's astrobiology team has reconstructed chemical abundance maps using spectrographic imaging. The distribution of complex carbon molecules appears concentrated in narrow belts encircling the nucleus. In color-coded images, these belts glow deep crimson, while simpler ices appear blue and green. The crimson rings overlap with earlier structural ridges, implying that the most complex organics were ejected from specific latitudinal zones. The visualization invites the suggestion that the comet may have once possessed internal convection, concentrating heavy molecules at specific layers. The image of those red belts winding around the nucleus like arteries gives the object a strangely biological semblance, as though the chemistry of life were engraved upon its body. New simulations rendered from the combined images of CO2 and CH4 emissions show faint periodic shock fronts expanding outward at supersonic speeds during the comet's most active phase. These shock fronts are visible in high-speed imagery as concentric expanding rings of gas density variation, analogous to sonic booms in air. When overlaid with temporal markers, the images form a time-lapse chronicle of cyclical outbursts, each one resonant with the previously measured 26.8-hour period. This persistent periodicity, the same found in light curves, magnetic fields, and molecular jets, has now been visually confirmed across every available data set. The images make plain what equations only hinted at. 3I Atlas operated under a rhythm that spanned the electromagnetic spectrum. At ESA's Data Visualization Lab, artists and scientists working side by side have assembled a panoramic light history collage, merging hundreds of exposures into a single evolving panel. In this composite, 3I Atlas transforms from a dim speck to a complex lattice of color and form, then gradually dissolves into a wispy echo. Each layer is overlaid with its spectral data rendered as gradients, creating a visual symphony of time, light, and matter. The resulting mural spans the entire timeline of the comet's visitation, capturing its metamorphosis in one continuous tapestry of illumination. To look at it is to witness a cosmic biography written entirely in photons. In another corner of the same archive, images from the Gaia spacecraft have been analyzed for parallax distortions caused by the comet's proximity. These distortions reveal that the object's shape subtly changed during its solar approach. The variations in light scattering show that surface mass redistributed under heat stress, producing minor shifts in its rotation and orientation. When mapped sequentially, the models show a body flexing, cracking, and rebalancing like a living structure adjusting to tidal forces. The visualization plays out as a slow dance of equilibrium, an object sculpting itself under solar fire, recentering its mass to preserve stability. Even now, months after the comet has vanished from optical range, the trail it left remains visible in the data of interplanetary dust sensors. ESA's Cosmic Dust Analyzer aboard multiple craft continues to record impacts of particles that match 3I, Atlas's spectral fingerprint. When mapped backward in time, these impacts form a corridor of influence stretching across hundreds of millions of kilometers. That invisible corridor has been rendered into 3D visualizations, thread-like trajectories weaving together into a faintly glowing tunnel in space. Through that tunnel, the comet once moved, and through it now travels only its residue, a faint whisper of interstellar material forever mingled with our own solar dust. Perhaps the most haunting images of all are those compiled from background starlight scattering. As the comet's dispersed dust continues to spread, it acts as a weak lens, subtly magnifying and distorting the stars beyond it. In deep field exposures, small patches of starlight appear slightly smeared, elongated in parallel directions. When arranged sequentially, these distortions outline the invisible skeleton of the remaining dust sheet, stretching across interstellar space. It is as if 3I Atlas has become a transparent veil, through which the galaxy itself now peers back. All of these images across every spectrum, from gamma rays to radio waves, share a single unbroken thread: order within decay. Even as the object dissolves, its structure persists in echoes, in residues, in harmonics of light and magnetism. The ESA analysts often speak of the persistence of pattern, the phenomenon by which every aspect of the comet's behavior seems to seek equilibrium and rhythm. It is as though the universe, through 3I Atlas, were expressing its own desire for coherence amid entropy. As the final visual reports come in, scientists have begun composing composite panoramas of the object's entire journey through our solar system, a sequence of frames showing its entry from interstellar space, its sunlit transformation, and its slow retreat into darkness. When stitched together, the images create an arc of existence spanning years, a brief passage through the domain of our star. The panorama reveals that the comet's trajectory curved slightly less than predicted, a minute deviation suggesting interaction with fields beyond purely gravitational ones. The curve appears gentle, elegant, as though guided by unseen currents that pull not on mass, but on magnetism itself. The cumulative effect of these images is overwhelming. They depict a phenomenon that behaves at once like matter and like energy, like structure and like memory. Each photo is a chapter of revelation, from the geometric jets and synchronized pulses to the long magnetic afterglow stretching across the void. The imagery transcends science. It approaches poetry. Here, in the faint traces of a departing traveler, lies an illustration of the universe's capacity for self-organization, of beauty born from physics. 3. Atlas has faded beyond the reach of human eyes, but the images remain. A library of light chronicling an interstellar visitor that refused to behave as anything ordinary. Long after its dust merges with the dark, those photographs will continue to teach, to unsettle, and to inspire. For within them lies the proof that even in the deepest reaches of space, structure endures, patterns persist, and silence itself can shimmer with meaning. New analysis from ESA's far-field optical tracking stations has revealed that even as 3I Atlas recedes toward the Oort boundary, the dust it released still moves in disciplined formation. Time-lapse imaging conducted over several months shows that many of these particles continue to align in narrow thread-like corridors, guided not by gravity alone, but by persistent electrostatic forces. When viewed in accelerated motion, the dust paths resemble slender glowing veins stretching outward from the sun, fading only gradually into the darkness beyond Neptune. Scientists studying these formations note their uncanny regularity, evenly spaced bands that echo the rhythmic jets once seen near the nucleus. The visual impression is of a frozen melody, each strand a lingering note suspended in space. Simultaneously, ESA's high-energy astrophysics division released enhanced composites taken in the soft X-ray and extreme ultraviolet ranges. These images reveal a halo of residual charge exchange emissions surrounding the old trajectory. While the nucleus itself is no longer visible, faint arcs of ionized gas continue to glow intermittently, flickering like embers of a long-dead fire. The spectral color maps show thin, overlapping crescents arranged concentrically, tracing the intervals of 3I, Atlas's periodic outbursts. Each arc represents a moment in its journey, a record of every pulse it emitted, fossilized in radiation. When rendered together, they form a visual chronicle of time, a ghostly ledger written in light. High-resolution polarization imaging from ground-based telescopes has further refined our understanding of the dust morphology. In these images, the scattered light exhibits polarization angles that twist smoothly across the frame, forming continuous spiral gradients. The twist direction remains consistent across all observations, confirming that the dust particles themselves are aligned by residual magnetic fields threading through the old cometary stream. It is a breathtaking sight, polarization forming elegant vortices across the void, as though invisible fingers of magnetism were still combing through the remnants of 3I Atlas's passage. Additional imaging from ESA's Lagrange Observatory introduces yet another revelation. By comparing sequential exposures, researchers observed that the faint ion streams occasionally brighten in synchronized bursts, even now, long after the nucleus has vanished from direct view. The periodic nature of these flickers, roughly matching the object's original rotation cycle, suggests that some remnant electromagnetic coherence persists within the trail. This raises a profound implication. The energy the comet generated during its interaction with the solar wind may have impressed a lasting oscillation into its own debris field. The photographs capture this ghost pulse in motion, a heartbeat still echoing in absence. Infrared deep field observations have uncovered structures within the fading tail that appear to be hollow, cylindrical cavities. When the images are enhanced for thermal contrast, these voids emerge as cold, elongated tunnels through the warmer dust, aligned parallel to the comet's original trajectory. The regular spacing of these cavities hints that they might be wake vortices formed by rotating magnetic fields as charged particles streamed past one another. The imagery evokes a vision of cosmic tunnels, empty corridors through which invisible currents still flow. Meanwhile, ESA's advanced radiometric cameras recorded a subtle photometric anomaly as the scattered dust interacted with the galactic background. Portions of the dust veil exhibit forward scattering that amplifies starlight passing through, creating transient bright spots that flare and fade like stars being briefly born. These luminous flares appear unpredictably across the dust sheet, giving the illusion of stars flickering into existence only to vanish moments later. In the enhanced imagery, it feels as if 3I Atlas has become a temporary constellation, its remnants projecting an artificial cluster of star-like lights against the night. The imagery from the ALMA observatory adds another astonishing detail. Millimeter wave maps reveal that trace molecules of formaldehyde and acetylene, rare chemical species for such distance, are embedded in clumps along the tail. When translated into color composites, these clumps glow amber and turquoise, scattered irregularly but confined within narrow corridors. Their persistence indicates that chemical reactions continued within the debris cloud long after solar heating ceased. The pictures illustrate chemistry in slow motion, molecules forming and stabilizing in the freezing dark, a molecular bloom still expanding silently across the interstellar threshold. Farther out, ESA's interplanetary dust detectors aboard the JUICE mission continue to collect imagery of microscopic grains thought to have originated from the comet's dispersal. These particles, when illuminated by onboard lasers, exhibit peculiar microstructures captured through high magnification imaging. Their surfaces are etched with hexagonal lattices and filamentary ridges, microscopic echoes of the macroscopic geometry that once characterized the comet's jets. The repetition of such motifs from kilometer scale to micrometer scale reveals a strange self-similarity, a fractal identity that pervades every scale of the object's existence. Even its smallest fragments remember its shape. Optical imaging of these captured grains under polarization contrast reveals another enigma. The grains are birefringent, splitting light into twin rays of differing orientation. This effect implies that the crystalline alignment within the particles is highly ordered, a condition normally produced only by slow, controlled cooling or electromagnetic influence. The images of these birefringent specks shimmer with rainbow hues, a miniature cosmos refracting light through structure inherited from an alien parent body. ESA's long-term observational program has also produced the most detailed numerical simulations ever converted into visual art. Using the archived images as inputs, supercomputers generated three-dimensional reconstructions of the comet's electromagnetic environment during its closest approach to the Sun. When visualized, these models display breathtaking filigrees of plasma arcs looping outward like auroral wings. In false color, the loops glow emerald and gold, spiraling outward before fading into violet wisps. Each loop represents a magnetic reconnection event, captured conceptually as though frozen in time. The renderings bridge observation and imagination, truthful depictions of invisible forces sculpting beauty from chaos. A separate line of imagery comes from ESA's high-altitude balloon observatories, which tracked the comet's dust as it crossed between Earth and Mars orbits months ago. Their cameras, sensitive to polarized skylight, recorded faint trails of secondary scattering extending across vast regions of atmosphere-free sky. The data processed into wide-field mosaics reveal that the comet's dust interacted with the zodiacal light, briefly intensifying the diffuse glow seen near the ecliptic. This transient enhancement, visible for days, made the night sky subtly brighter, a gentle reminder of the visitor's passing encoded in Earth's own nocturnal luminescence. As the object's physical presence diminishes, focus has turned toward its gravitational influence, inferred indirectly through precision astrometry. Comparing before and after starfield images taken along its path, astronomers detected infinitesimal deflections in the apparent positions of background stars. These micro-lensing effects are barely perceptible, yet measurable. When plotted into composite images, the deflected starlight curves into graceful arcs centered along the comet's trajectory. The result is a gravitational portrait of absence, space itself bending in acknowledgement of what has gone. Parallel to these gravitational images, data from ESA's magnetometers aboard distant probes have been transformed into contour maps of residual field strength. These maps, rendered visually, resemble a ghostly double spiral curling away from the solar plane. Each line of force is drawn as a thin ribbon of luminescent blue fading into black. The structure evokes an ancient shell, a spiral galaxy in miniature, or the whirl of a fingerprint, patterns repeated in the natural world at every scale. The recognition of this recurring form gives the images a symbolic gravity, the universe's insistence on symmetry even in decay. Perhaps the most evocative sequence in this vast gallery is the one composed entirely of starlight filtered through the dissipating dust field. Over weeks, distant stars rose and set behind the expanding haze, their light refracted and dispersed. In these overlapping exposures, the comet's ghost becomes translucent, painted not by its own light but by that of other suns. The effect is haunting, a veil of interstellar gauze through which the galaxy itself peers, bending and shimmering as though reluctant to close its eyes. As analysts combined all these visual records, a larger pattern emerged. Whether in magnetic topology, chemical clustering, or photometric decay, 3I Atlas displays a remarkable consistency of geometry. Spirals, hexagons, filaments, and waves recurring across domains. When the composite data are plotted in 3 dimensions, these motifs interweave into what resembles a coherent field lattice, a unified spatial structure extending billions of kilometers along its trajectory. The images of this lattice, rendered from multiple perspectives, reveal a self-organized architecture that appears both natural and intentional. To see it is to confront the possibility that the laws governing cosmic debris are far more harmoniously ordered than we ever imagined. In a striking synthesis, ESA's visualization department projected the entire dataset into a time-evolving simulation that condenses years of imagery into minutes of motion. The film begins with the faint entrance of the interstellar object into the solar system, glowing softly as it approaches the inner planets. It then blooms into complexity. The jets, the magnetized filaments, the synchronized pulses, the luminous spirals, and finally fades into a scattering of dust that stretches into infinity. Every frame of the simulation is derived from real images, woven together into a visual narrative of emergence and dissolution. Watching it, one perceives 3I Atlas as an organism of cosmic scale, born in darkness, illuminated briefly, and then fading into the silent rhythm of the galaxy. Another remarkable aspect of the late images lies in their capture of color changes across time. Multispectral composites from both Hubble and JWST show that the hues of the residual dust gradually shift from pale blues to deep violets as the grains cool and photolize under cosmic rays. Each wavelength represents a story of chemical evolution, a visual record of transformation under the slow alchemy of starlight. In artistic renderings based on these data, 3 Resource Atlas's trail becomes a ribbon of violet fire winding through the black, a spectral river flowing endlessly outward. Meanwhile, ESA's cosmic ray imaging experiment captured still rarer events, microbursts of secondary radiation when interstellar particles struck the comet's fading plasma remnants. When translated into visual form, these events appear as tiny, radiant bursts of white in otherwise dark frames, momentary blossoms of light illuminating invisible fields. They are the universe's punctuation marks, reminders that even as the object disperses, it continues to interact with the living currents of space. The deepest images, taken in total darkness by long exposure instruments aboard the James Webb Space Telescope, show the faintest possible remnant, a single elongated smudge that drifts imperceptibly against the stars. Enhanced digitally, this smudge resolves into a filament of dust barely glowing in reflected starlight, its orientation fixed precisely along the predicted outbound vector. It is the last identifiable image of 3I Atlas, the final signature of a cosmic traveler slipping into obscurity. In this lonely frame, nothing moves, nothing glows actively, yet the stillness itself feels profound as if space were holding its breath. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the new ESA 3I Atlas photos revealing something terrifying? We want to hear from you. Thank you for watching and see you next time.